Good afternoon, everyone. A hearty welcome to all the participants on the second day of the training program. I hope everyone is enjoying the ride on the Knowledge Express under the guidance of our master trainer and expert faculty members. So ladies and gentlemen, please fasten your seat belts and let us begin the ride. I would now request Professor Sunil Jha sir to please take over and brief about today's sessions. Over to you, Professor Jha.
Thank you, Naman, for the nice start, and good afternoon to everyone. And certainly, I hope that you enjoyed yesterday's session, and we are now ready to take over the next day of the training today. So before we take up the technical session for the day, I would like to quickly brief about what we have planned for today. So today's session, as you can see from the course schedule also, after finishing the basic understanding about the convergence of the automation and IIoT, and today we will be going to discuss more about the smart sensing for Industry 4.0. And we have also planned a small lab demonstration for you how the smart sensors can be interfaced with the PLCs as well as the IIoT platform. So that will be for the first session. And then we will be having a next session focused on the smart machines. And as you know that we are again emphasizing on following up these activities which are aligned on the e-learning platform. So as you can see the detailed schedule over here. So we have first session starting after my briefing up to 3:15, the smart sensing for Industry 4.0. We have an invited speaker from the industry, Mr. Sudhanshu Control. Then post that I will continue with the discussion on industrial IoT, and then smart sensor interface demonstration is aligned for you. And after the break, we will be talking about the smart machine. So we have again next invited speaker, Mr. Pankaj Aswal, joining for this talk. And then he will also be giving a demonstration of the smart machine implementation. And subsequent to that, I will be discussing about the smart machine implementation technologies, how we can do that. So that is all planned for today. I hope you will enjoy all these sessions. I just want to brief about the participation till now, because I will be observing the progress that is on the FSM Skills website. So I found that the pre-course assessment completed by 24 participants till now. Good that the same people have also completed the smart manufacturing quiz. So this number is right now coming out of 36. So I'm again insisting that please, those who are not doing this task, I will be submitting my report to FSM-NAIR that this is what the participation from all the people in the course. So please participate in all the activities. I also insisted you to complete this IIoT survey. So I just collected this statistics at around 12 o'clock. Maybe some of you might have submitted later on also. But the IIoT survey filled by only 16 people till now. And these are the assignments I have given. So again, the numbers are quite low as compared to the total number of participants in this course. So I will again requesting all those who are able to access the e-learning material on FSM Skills website. So barring 2-3 people whose accounts are still having some issues, I was just waiting for the data in the right format to create their accounts. I will be expecting at least the 30 and participation should be there in this course till now. So this is just a quick summary of your participation. I look forward more active participation and completion of these activities. Before I take it forward, just a short quiz here. So if you can see, if you have gone through the e-learning content, this is just to get a quick assessment on that. So I will be just throwing a poll to respond to this question. Let's see that how much you have gone through the e-learning content. So this quiz has nothing much to learn about a smart manufacturing, but just to get a quick assessment of that, whether you are looking at the content that we are sharing with you. So there's a good storyline of this Mr. Samrat Kumar that I was mentioning about yesterday. And against that, the whole concept of the smart manufacturing is being explained through that. So if you have gone through any of the content of that presentations or that recorded one, you should be able to answer this question well. So let me see that the response coming in. So we have 7 people given their input. So I will be expecting at least all those who are in the meeting should respond to this question. Good. So response is increasing. So I got 50% response till now. So rest of you also should at least punch your response, whatever you have understood and whatever you have gone through. So I'm waiting for another 5-10 seconds to just see all the responses over here. Good. So let's wait for a few more response to come in. Not a difficult question. If you have gone through it, I think probably you will be able to respond to this question well. Nothing technical as such. This is just in a common sense that you have gone through the content. That's all. So I have received roughly 26 response, and then we'll be just ending the poll. And if you can see, the results are like this. So I'm sure that you are able to see the results of the poll. So may I request anyone to just respond? What is the correct answer for this? You can see from the majority as well. So I found that 46% of you are paying attention to what we are just sharing with you as a content. So Mr. Samrat Kumar owns an automotive component business, and that is what the introduction has been given in the beginning of the discussion on the smart manufacturing slide. So I will just request others, those who are still punching the textile machine, textile mill, the machine spares, please spend some time on the content that we are sharing with you. Certainly that will help you in gaining some more understanding about whatever we are discussing in these live sessions. The idea is that certainly we are not able to cover up all the key points of the content in the live sessions, because there are limited sessions with the invited speakers as well. That is the reason I have put all the recorded content on the smart manufacturing training that we are conducting from last almost 2 years by now. So that will help you actually in understanding the complete concept. So that's a first question. So now I will be putting the second question, which is little technical based on whatever we were discussing yesterday. So if you can just respond to this question, I'm throwing the poll again to you. Yeah, so which smart manufacturing characteristic prevent breakdown maintenance? So there are certain characteristics which we were discussing in the yesterday's session. So let's submit your response to this. Certainly you will find these characteristics are overlapping somewhere, but certainly one important characteristic which will help you in preventing the breakdown maintenance. So I'm happy that I'm getting a majority of the correct answers. That is really nice. So I received 20 responses by now. Yeah, so hopefully let's wait for another 5-10 seconds. Good, so I got most of the responses over here. So let me just end the poll over here, and I will be sharing the results. And certainly those who have punched in the proactive characteristics is the right answer for this question. Connected is certainly one which will be helping in reaching out to that stage, but that is not the correct answer. And agility will certainly not be there, because agility, we are talking about more product mix and the more configurable layouts over here. So proactive is the right response. That's the right characteristics for the prevention of the breakdown maintenance. Just in a short assessment over here. So rest of the quiz you have already attempted as a smart manufacturing quiz. So I will just look at the review. Next slide I had, just these people are not able to access to the course, or they have not access to the course. I'm just flagging the names if there's any technical issue in login, because I have not received as such the so Mr. Mohammed Javed has dropped, so certainly that I can remove. I have a replacement and for him, but rest those who are present in the meeting, if there's any issue in login, please let me know, because I will be reviewing whether you are able to log in it or not. So please log in into the FSM skills website, because you have already missed the day one activities that are being planned on this. So that is all from my side. Yeah.
Jha Saab, this my name Rajesh Gupta is appearing, but I am logging in this
Oh,
email
sorry.
address
Yeah.
was
Yeah.
incorrect.
So certainly, thank you. I think this is the correction that I have already done. So I will remove that also. Yeah. Good. So I know that because I have created and solved the problem for you. Thank you, sir. Thank you. Thank you, Naman. This is all from my side, just in a quick brief about today's session. So let's start the first technical session for the day. Over to you, Naman.
Thank you, sir. Moving forward, we welcome our first speaker, Mr. Sudhanshu Kantur from Pepperell Fox Pepperell Fox Factory Automation Private Limited, to guide us on the technical session on smart sensing for Industry 4.0. A brief description about Mr. Kantur. Passionately involved in the field of industrial automation for now about 2 decades, has been an avid software programmer in control automation. Sudhanshu has hands-on on the supervisory experience in projects involving PLCs, drives, remote, input-output, and SCADA-based system, machines, processes, plants throughout India and overseas. Have been leading technical and projects for the factory automation business vertical at Pepperell Fox India since 2008. Avid enthusiast on technology, especially in the domain of networking and data communication, Sudhanshu is working across the control platforms and leading implementation of Industry 4.0 solutions for Pepperell and Fox factory automation business in India. Over to you, Mr. Kantur, sir.
Yeah, thank you, Namanji. Please allow me to share my screen. Naman, are you able to see my screen now?
Yes, sir.
Okay, thanks, Naman. Thank you. Thank you so much for introducing me, Naman, and thank you, FSM, for giving me this opportunity to present. I would like to thank all the participants here also. Today, I would be giving you a small update or the technology update on what has happened in terms of smart sensing solutions for Industry 4.0. To begin with, let me give you a brief idea about what we are going to talk about. Today, we will be discussing more on sensors. We all know about the control system. The control system components, basically, there are majorly 3: input devices, output devices, and a controller. One of the most important devices today are for controlling the input are the sensors. So in this presentation, I would be discussing about how the sensors have evolved over the last couple of years and how they are helping us to improve our processes. To begin with, we all know what sensors are. Sensors are nothing but devices which convert a parameter into a signals which we can measure electrically. So it is nothing but change in the physical parameter which can be converted into an electrical signal, and these signals we can take it into our control system, and then we can do decision making concepts or controlling the loop of making a proper closed feedback systems. We can see sensors being used in almost all type of industries, whether it's manufacturing of engineering plant or automotive industry, mobile equipments, material handling, which is an industry which is coming up very widely in the world as of now, printing and paper, food industries, processes, packaging. So all type of machines which are being used or which are there in manufacturing, they use sensors for controlling the system of giving the feedback to control the machines. Now, in this presentation, I would be basically discussing about different technologies that are there behind the working principle of these sensors and how these sensors have evolved. When we look into the industrial application portfolio, we can see a couple of years down the line, major applications that we were seeing in industry were detection type of application. Detection means detecting the presence or absence of a component, whether they are present or not, and the sensor would generate a digital output or a signal. Now, this has now evolved into now measurement systems. That means not only the sensor senses the presence of a component, but also give you the measurement values. The measurement values in terms of how far the object is from that particular sensor. Further evolvement happened when it started giving you the position values. That means it can give you the exact position where that system is, how much, with a high accuracy of few millimeters. That is quite possible. Another foray of applications that we see in the industry today are basically identification systems. Identification systems can broadly be classified as technologies which use our RFID and barcodes. That means we need to identify an object, and based on the type of the object, we need to do a certain operation on that object. So that is what identification systems are all about. And lastly, are communications. That means what we are connected, what we are reading, what we are seeing, what we are able to detect, that is being sent into a higher end system, which is through wireless communication or through an IoT, or what we can say, or OPC UA, or internet connectivity. So these are the different type of developments that we have seen in terms of sensors. And today I will be giving you examples of all these technologies and all these type of products that are there in industry today. So we'll start off with a very basic and a very common product that is widely used in the industry, which we know as proximity sensors or electromagnetic sensors. Inductive sensors, as we all have used in a lot of applications, are used to sense metal targets. That means they are basic sensors which generate digital output. That means whether the object was present or not, whenever there is a metal target in front of it. We all have understood the working principle where these sensors are used. It works on the principle of electromagnetic induction. That means there is a coil inside the sensor. The coil generates an electromagnetic field. And whenever a metal target comes in front of it, the field gets opposed. As a result of that, the sensor generates an output which we take into our control system. That means the loop is now finished, or is now over. That means we have sensed a metal target in presence of it. So these sensors we have been using in a lot of industries, as they are very basic sensors. One of the applications that we have seen in the industry are where we sense the wheels of a wagon. That means the wheels of the train that is coming by. This is an application that is what we have seen in a metro, a daily metro, or a DMRC application. You know, all these trains, as they are moving on a platform or on a track, they need to be lubricated. There is a lubrication pump which is attached inside it, and at certain point of the time, we need to do the lubrication. So these sensors are mounted on the track. As and when the wheel comes in that area, that means the train has just arrived or it's there, it gives a feedback. The feedback goes to the controller. Controller opens and it generates an output, so that the lubrication of the wheel happens in the system. So this is a basic sensing application where we sense only the presence or absence of a metal target. And based on that, we take a call and we do a certain operation. So this is one of the applications. Similarly, a lot of applications where we need to detect the presence. Weigh bridges are one of the application areas. We weigh the load which is being carried on a train. Now we need to measure the weight of that truck or weight of the bogie. When a wagon arrives at that weigh bridge, we need to take a feedback. When the wheels are at a proper location, then only the feedback should be taken. Then only the weight should be taken and taken into the controller. So these sensors make sure that they sense the wheel in a proper position. A combination of multiple sensors positioned at different distances enable the presence of the wagon at the right position or the appropriate position, thereby taking the weight of the wagon and then giving it to the controller to make a decision to store that particular wagon has got this much of material stored into it. So these are some of the common applications that we have done and we have seen in the industry which uses a common proximity sensor. Now, as I was saying, these sensors are working on a principle of electromagnetic induction. There is a coil in front of it, a metal coil which generates an electromagnetic field. Now, when we say the evolvement, the sensors have evolved, what we have done is, what we have seen in the industry is, instead of putting a single coil, if you put a multiple coils inside a housing and enclose that housing, and behind that housing, we have a fine microcontroller attached to it. So it becomes a multiple inductive coil systems. Now this system helps us to not only sense the presence of metal target, but also generates an analog output based on the position of the target. So what we can do with this is we can do a lot of applications related to positioning of the object. That means these sensors can now not only sense, but can also generate analog signals. And these analog signals, we take it to the controller to know the exact position of the metal. So this helps in doing positioning. How they work, we have a metal target which moves parallel to the surface of the sensor. And when it moves parallel, the sensor generates analog output. A common example would be, for example, let me say, we have a sensor of length of 100 mm, and we have a metal target, which is a normal mild steel target, which is moving parallel to the sensing face of the sensor, thereby generating 4 to 20 milliamperes across 0 to 100 mm length. So a lot of positioning applications, linear valves, linear actuators, they use this type of sensor for linear measurements. Similarly, if we arrange the coil, which is again the heart of the system, in a circular manner, so we can do angular positioning. Again, it's the same concept. There's a metal target which moves across the circumference of the sensor. And when it is moving across the circumference of the sensor, we are generating 4 to 20 milliamperes as an output. And when we calibrate that, we get 0 to 360 measurements with an output of 4 to 20 milliamperes. That means angular measurement is also possible. So how the sensors got evolved? A single coil system made developments into a multiple coil system. Single coil was able to detect the presence or absence of a target. With multiple coil, we are not only sensing the presence of a target, but we are also giving a analog value. Moving on, another concept or another type of sensors which are widely used in the industry today are photoelectric sensors. As the name itself says, photoelectric, these sensors work on a principle of light. That means there is a light inside the sensor which is emitted. The light falls on an object and gets reflected back. And based on the light intensity which is received, we are able to detect the presence or absence of an object in front of it. Now, these sensors, this was what a simple technology was all about. If the light is obstructed from reaching the receiver, that means there is an obstruction, there is a presence of an object in front of it. Now, what has happened is, if you have a multiple transmitters arranged inside a housing, and this housing, you have multiple receivers on the other side, these sensors will not only sense the presence, but will also be able to do the measurement of the objects. So these are basically light grids, which are widely used in the industry today for measurement of the height of an object. That means if you have an object which passes through this light grid, not only we can sense the presence, but we can also measure the height or width of an object which is moving by. And these transmitters, the LEDs are so positioned that we can do it with an accuracy of 3 mm. That means with a high accuracy of 2 to 3 mm, we can measure the height of an object and give an output, which is on a communication bus. So these type of photoelectric sensors are widely used for height measurements in logistics applications, where we have containers moving in and moving out, whether it's filled or empty, they all detect the same and then generate an output. Similar type of photoelectric sensors, which we also call as diffuse type of sensors, these sensors consist of a transmitter and receiver in the same housing, are also used in automatic doors and elevators. If you approach a simple example where we can see these type of sensors are, when you approach a shopping mall, you can see the door opening automatically. So they have these type of photo sensors mounted at the top of the door. With these sensors sense the presence of an object and then they open the door. The same concept is also being worked into in railways for our Indian developed train, Vande Bharat. So they are working, we have a couple of vendors who are working, who are developing the doors for it, where they are trying to make automatic doors. And for automatic doors, they are trying to use these type of sensors which can fit on the top of the door, which can sense the presence of an object. And based on the presence of that object, the door automatically opens. So allowing free movement of the persons inside. So these sensors, they work on the principle of light. So that's why they are said, told as photoelectric sensors. Another category or another aspect of sensors are ultrasonic sensors. Ultrasonic sensor, as the name itself says, work on the principle of sound. These sensors generate high frequency sound waves, which travel at a speed of 344 meters per second. That is what we say the speed of sound. And when it hits the target, the sound waves get reflected back. The reflection which is received back is known as the echo, which are measured by the receiver of the sensor, and based on the time of flight, that means the time taken by the sound waves to travel, hit the target and get back to the sensor, is calculated, thereby measuring the distance of the object in front of it. Ultrasonic sensors, again, they are widely used in the industry for level measurement, for height measurement, for detection of an object in front of it. The biggest benefit of these sensors, why these sensors are becoming more and more used in the industry today, are because they are color neutral. That means sound waves are not dependent on the color of an object. The reflection of the sound waves are not dependent on the color of the object. That means any colored object can reflect the sound waves back, which was a drawback with other sensors. I discussed about photoelectric sensors. When I talk about photoelectric sensors, as I said, these sensors work on the principle of light. So we all know the basics of physics, that a dark color object will absorb all the light, whereas a light color object will reflect maximum light. So if there is a target in front of it, which is wearing a black, which is black in color, the sensor may not be able to sense it from a longer distance. But this limit of not working with different colors was solved using an ultrasonic sensor, because ultrasonic sensors would generate sound waves, and these sound waves were color neutral, so they will not be affected by the color of the object, and they will be able to detect any type of an object in front of it. So these sensors are widely used in applications where we need to measure the level. One such application is measuring the level inside the wagons. This is one of the applications that we have done for a steel industry, which has this train, which is carrying a raw material. The raw material is a form of uh, 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 coal or coke, which is carried from the mines. And here we need to check whether that level, how much this wagon is filled, whether it's half filled, full filled, or empty. And for that, none of the sensors would work properly if they are not ultrasonic sensors, because photo sensors, as I said, will not be able to detect the difference in the colors. So ultrasonic sensors mounted at the side or mounted at the top were able to measure the level inside the tank, inside the wagon, and then generate an output. Based on that, we can now check whether it was half filled or fully filled or empty. These sensors, they have a flexibility of giving you analog output also. That means you can get 4 to 20 milliamperes as an output directly. So that was one of the applications which is being done for checking the level inside the wagon. Secondly, another application that we come across, because most of the wagons which are being used in the industry, they are very old, and over a period of time, the wall of the wagons, they bulge out. They bulge out because of the load that is being carried inside it, because the material which is there is dropped at certain height, and as a result, the walls of the wagon get damaged. So when the wagon is entering into a house, should be within a certain bandwidth, else it can collide or it can crash with the wall and damage the whole structure. So again, these type of sensors are mounted on the side of the wall, on the sides, and they check the distance between the sensor and the wagon. If the distance is proper, they generate an output. If there is a change in the distance, they generate a second output, which means there is something wrong with the wagon. Correction has to be done. Make sure that the wagon doesn't enter this particular zone, as it may result in crashing with the wall. So these are some of the common applications that we have seen. One of the applications which I can think of, I don't know whether it would be feasible option or not, could be to check the level of water inside the tank. We have seen a lot of applications being done in the industry today, where we have these huge water tanks. We have to check the water level, not only in the industry, but it is also being used in the commercial world. All these dam or water reservoirs, they check the level which is filled inside the dam reservoir before opening the dam, the penstock of the dam, to let the water go out. So again, these ultrasonic sensors are mounted at the height. They can detect the object, they can detect the level of water, and based on that, they generate an output. So these are some of the very common applications. The biggest benefit is these are color neutral. They are not dependent on the color. They can be used in outdoor environments, open environments, as they do not have an impact, or the dust or other things will not impact the working principle of the sound waves. Now, another product which is widely also used in the industry are encoders. Encoders, as we know, are the devices which convert mechanical movement or mechanical information into an electrical pulse. So it is nothing but a small shaft which is connected to a rotating disc at the back, and the disc is having slots in it, and there is a photoelectric system or a photodiode which is attached to the disc. So when the light passes through it, it will generate a signal that is on, and when there is an opaque part, that means where there is no slot, it will generate 0. So based on that, we get pulses. So in one rotation, we get number of pulses in it. So if a encoder or a device or a tachometer is having 100 slots, it will generate 100 pulses. So generally used for applications for speed monitoring, for angle calculations, for linear positioning of the object, encoders are widely used in the industry. So every motor, if you want to have a control feedback, if you want to know the speed of the rotating device, is always used using an encoder. Moving on to the latest trend that is going on in the industry today are RFIDs, or what we call as identification systems. Identification systems can basically be classified into two types. One is uh, optical based identification system, where we talk about barcodes, barcode readers. And second is radio frequency identification, which is using RFID, that is a radio frequency for doing an identification of an object. Now this radio frequency identification systems, they come in different frequency ranges. Why and where do we use this radio frequency? When we need to do an tracking and tracing of an object. We have a lot of objects. We need to know how old that object was, where it was, and when it was manufactured. If we want to know the genealogy of an object, that is where radio frequency identification systems comes into picture. Uh, a simple RFID system may consist of three basic components. There is a tag, there is a controller, there is a RFID reader. So the tags are the devices which are attached to a component, where all the information related to that component is stored. The reader, which is the second part, reads the information wirelessly from the tag where this information is stored, and then it transfers it to the controller, wherein it can go into your high-end system, which is your PLC or a PC-based system. So when we see the basic applications, it is either tracking or tracing or identification. When I mean identification, I mean to say is that we need to identify an object in a line, and based on that object, we need to do certain operations on it. So sometimes, most of the times, or we can see there are objects which are very similar to each other with only a slight parameter difference. So how do we identify these objects? So what we can do is we attach these type of RFID tags or transponders, which they are called, to that particular device, write that information onto it, that this is product A or this is product B. The reader will, whenever the product comes in range of this reader, it will read it and then transfer that information directly to the controller. So this is what an RFID system is. So RFID comes in different frequency ranges. Short range is 125 kilohertz and 13.56 megahertz. And long range RFID are those which are working on ultra high frequencies, which is 865 megahertz to 867 megahertz. So this is the frequency which NHAI or the government of India has finalized for use in electronic toll collections. You must have seen those fast tags, or you must have seen those tags which are pasted on the windshield of your vehicle. And when you approach an electronic toll, the reader which is mounted at the top reads that information from the tag, and based on that information, the toll gate, the door opens, and it allows you to pass. So the tag contains all the information related to your vehicle, the amount which is there in your balance, which is there in your tag, and thereby allowing you to move. So UHF is those technologies. We also see a lot of UHF readers or other readers being used in shopping malls when we have a small product and each of the product has a small tag attached to it, which we need to disengage before coming out of the mall. So again, these all are applications related to identification of the object. Tracking of the object would mean when we have a manufacturing line from the raw material to the finished product, the product has to go through different phases or different operations, and at the end we have a finished product. So each and every parameter of the operation that the product raw material went through before a final product was manufactured has to be recorded. Generally, what is being done in the industry today, they keep the paper trail. They have a bin, they have a paper trail wherein they write in all the informations, which is now being replaced by using RFIDs. That means our RFID tag is attached to a component. As the component moves from one point to the next point, all the information, all the relevant operations that has been done on that component are stored into the tag. And at the end of the cycle, that is at the end of the production, all the information is taken back from, is read back from the tag and stored inside the servers, thereby maintaining the genealogy of the product from the raw material to the final finished product. So this is what RFID systems can help in the industry. Let me share with you a couple of applications that we have done or we have seen in the industry. Uh, Identification and tracking, as I was saying, is a very common application. Since you all are from the railways, you must have heard about this TCAS, that is Train Collision Avoidance System. So what we do in this is we have a reader which is mounted below the engine. The reader has to read a tag which is mounted on the bed of the track. And when the train approaches, the reader which is mounted will read the tag and give the information to the controller of the engine. And from the engine, it gets to the centralized location. That means this train has reached a particular location. So if there are two trains which are approaching on the same track or nearby to each other, the location is automatically transferred. And based on that, the controlling can be done. This was a project, I don't know at what stage it is as of now, but this was a project that was started a few years back where RFID was considered as an option for collision avoidance. Another thing which I've also seen is the same system being used for, there are certain engine, I don't know the exact word, please help me out with that once after this. There are small engines which control, which has got equipment inside it, which are supposed to monitor the track of the particular route. And this engine is equipped with all type of equipments for checking whether the track is fine or not. So again, if there is a problem at certain locations, how do we identify that? So here again, the tags which were mounted on the beds are used. The reader reads the location, and based on the parameters, if all the equipments, they know at which particular location the track was damaged or would require certain repair work to be done. So this was another application which I have seen being done in railways. Recently also, there was almost a year back, there was a information that was extracted that all wagons of the railways will have a tag mounted on the bogie so that we can identify the make, the manufacturing date, and all other parameters of that bogie. So they will also have a tag mounted on it. So again, that is again an RFID system where this information is stored, and based on that, we are able to know when that bogie was manufactured, and all other related information are stored inside that tag. So these are some of the common applications which I have seen being done where RFID is widely used. Again, in the manufacturing line, if I say from where we have a manufacturing line, we are manufacturing a whole component, or in our automotive industry, from the raw material to the finished product, we use RFIDs at different stages for different identifications or for tracking. Now, another technology today that is widely used are vision systems. We all know vision systems, which is nothing but a camera system with a lens and external light, which are supposed to check the quality of the product at the time of manufacturing, so that we are able to pinpoint the drawbacks or the wrong things that we have, so that the process can be, so that there is no wrong material going inside the line. So for that, vision systems are widely used. Now the vision system, they work in only X and Y axis if you're talking about a 2D camera system. But there are now new developments where we can see a 2D vision system which can not only do X and Y, but it can do X and Z axis. That means the depth of the component can also be checked and measured. These are known as light section sensors, or also we can say as profile sensors. They can check or measure the profile of the component, and if there is a variation, that means the quality is not up to the mark with what the ideal quality should have been. These sensors generate an output, and that output you can go or no go can be done. That means whether the component is passed or failed can be done. So these sensors are again not vision sensors, but they use a technology where they have a light section, that is, there's a laser line, and the reflection of the laser, which is coming from the object, is captured in a form of an image. The image is stored, it is broken into different pixels. The pixels are then matched, compared with the real-time object, which is coming in front, and pixel by pixel matching, we are able to check whether the object was same or not. So it can do a profile comparison of the object. That means the depth of an object can also be measured using this technology. So as common example, it's more related to a manufacturing industry where we have these engine shafts. These shafts have got small cams on top of it. The position of the cam, the depth, the height and width of the cam needs to be measured with fine accuracy. So if it is falling within a certain range, we say it is fine. That means it is a passed object. If it is going beyond a certain range, that means the object has gone, there's a wear and tear in the object, and object has to be rejected. So 2D profile measurement. So it can do a profile measurement of an object using a normal sensor, which is working like a camera. Now the same light sensor, uh, we always see a lot of these lidars being used. Lidar is nothing but a light sensor which is mounted on a rotating motor, thereby giving you the 360 measurements of distances by illuminating the target using a laser light. That means there is a light which is laser sensor which is mounted on a rotating motor, on a motor which is rotating at a certain speed, and thereby giving you distance measurement of the object. So that is what we call as a lidar, light detection and ranging. So what it can do, it can give you a 3D profile of a component which is just below it. And based on the 3D profile, we can check whether the component was okay or not. So in the picture and the second picture, as you can see, an application where we have a robotic arm and there is a 360-degree lidar. As the robotic arm moves, the lidar scans the pallet and identifies the empty object inside the pallet so that we know the robot has to place another carton inside at this particular location. So this is what we can do using a lidar sensor for doing measurement. These type of lidar sensors are widely also used in industry in material handling where we have these AGVs. Today we talk about AGVs moving and AGVs are automated guided vehicles. These vehicles move from one point of the plant to the other plant carrying the material, raw material, without any operator on it. So lidar sensors are again used for the navigation purpose. Same thing can also be used for profiling of the component. There is a simple application example where we use this type of lidar to check whether this particular truck is empty or not. Since the lidars are rotating at a very high speed, we are able to generate a point cloud. We are able to pick up the points and measure the distances at each and every degree. And based on each and every degree, we are able to get the distance of the object. And based on that, we are able to make the profile of the whole truck. So we can know which area was empty and which area was filled up. So this is an application where lidars are widely used. The picture on the right hand side is nothing but blue and red dots. It is nothing but a point cloud. These are the points that we have captured using a lidar scanner. And when we add a color to it, that means using a lidar and a color camera, we can also get the whole profile of the object. So this is nothing but a side profile of a vehicle, that is a car. Here you can see the walls of the car and the side screen of the wall of the car being captured using a normal lidar sensor. Moving on to some special sensors, vibration is one of the most important aspects today. We need to do a condition monitoring application. That means we want like to measure certain key parameters of the object, of motors that are being used, and vibration is one of them. So vibration sensors measure the amount of vibration that is there, and based on the vibration, it will generate an 4 to 20 milliamperes output. So these sensors are equipped with the MEMS technology. That is, it consists of a small micro electromechanical system inside it. That's a small chip of a size of 2 by 2 mm roughly, which can measure the vibration which is caused because of the movement of the mass. So this system basically consists of a spring, this system is basically working on a spring mass balance. That means there is a small mass in the middle, and there are, which is attached by springs at four sides. So when there is a vibration, this mass moves from one point to the other in x-axis or y-axis, resulting in measurement in x and y. So that means we can measure the vibration of any component, if there is a vibration in any component, to what level, by generating 4 to 20. So it's working on a change in capacitance principle. That means the mass having a plate attached to it acts as a capacitor, and then when it moves, there is a change of capacitance which is happening, and which is then converted into an electrical signal wherein we can get the measurement values. So vibration measurement is one of the condition monitoring applications where we check whether the vibrations are within the limit. If it has gone beyond a certain limit, we need to stop and do the maintenance of that object. These are some application of these type of sensors. Like vibration measurement is one. Same concept is also used for angle measurement or tilt sensors, as we say. So same concept with the same MEMS principle, with the same spring mass balance is mounted inside the sensor. So as we are tilting the mechanism, the sensor gets tilted and the spring mass moves in that particular direction, thereby giving you the tilting angle of the object. So for angle measurement, tilt sensors are used, and these tilt sensors again work on MEMS principle. Another type of positioning system that is widely used in the industry today are known as optical based positioning systems. We have a wide variety of products which are moving at high speed, and we would like to do the positioning. So what this positioning system does is it consists of a camera which reads a barcode. So instead of a single barcode, there is a strip of barcode which is attached along the path. And as it moves along that path, it reads the barcode and generates an communication signal. That means on a communication bus, we get the exact position of the object. And with this system, we are able to generate a high accuracy of 0.1 mm with it. That means with heavy accuracy of 0.1 mm, we are able to position that object in a moving conveyor or a moving system. So this is an application that is widely used in storage or moving systems. You can attach this system to a camera-based system to a device which is moving either X, Y, or X, Y, Z in either of the directions. And as the camera moves, it reads the barcode and generates an output. The same concept is also used for AGVs when it's moving on the floor. So it can read the barcode, it can generate the position, how much distance I have traveled from home position, and to what distance I have reached. So these were something on different type of sensors, different type of positioning system, measurement systems, identification systems that are there in the industry today, and how these systems can help you to do a lot of applications. Now I would just give you a feedback of how these sensors have now evolved further into what we say can help us to do Industry 4.0 applications. When we talk about Industry 4.0, we all know it is about connectivity, where all the information is available. It's more about data exchange. So all the data. So sensors, as we know, fall at the lowest level of the network topology, or we say the automation pyramid. So these sensors earlier were supposed to only communicate with the PLCs which were there at the top, or the controllers which were there at the top of them. That was at the device level. So this information would never directly go to the ERP systems or to the plant level MES systems directly. But now these sensors are so developed that the field devices which were at the lowest level of the hierarchy can now communicate directly to the ERP system, to the plant at the plant level, or also to a handheld smart devices. So these systems or these sensors at the lowest level, they did not have any service data. That means they were only able to transfer a signal which was in the form of digital, that is 0 or 1, or analog signal which was in form of 4 to 20 milliampere or 0 to 10 volts. That was only a one-way communication. So now, since we are talking about Industry 4.0, that means we want these sensors to become more smarter. So they should not only transfer the information, but they should also be able to receive the communication. That means it has to be a more of a two-way communication with them. Plus, they should have a memory inbuilt into it. They should have an identification. They should have an identity. They should be able to identify it themselves. They should be able to do diagnostics. That means if a sensor is about to fail, the sensor itself should give a feedback that I am going to go down, and based on that, the sensor can be replaced before the actual failure happens. So all this is now possible with a technology that is being inbuilt into a sensor, which we call as IO-Link technology. IO-Link is a communication technology that is nothing but a small chip which is added into the sensors, thereby making them smart. So what these sensors can now do, it can not only transfer the basic values, that is the digital signals, but it can also do diagnostics at the sensor level. It can do continuous communication with not only the PLC, but it can also transfer the information directly to the controllers at the plant level, or directly to the cloud. Another benefit is with this technology, it's a bi-directional communication. Like I said earlier, the sensors were doing only one-way communication. They were only giving you the feedback. But now the controller can talk to the sensor, can give them a command to reply back, and based on that, the sensor can transfer the information back to the controller. So what all we can do? So there are a lot of other parameters apart from the process values we can get from the sensor. We can get the health of the sensor. We can get how many hours the sensor has been working. We can change the parameters of the sensor remotely by sitting at a remote location. We can get all servicing parameters. All those parameters are now available inside the sensors. And for that, we are no more dependent on PLCs to do it. We can do it remotely by sitting at a remote location. From my control room, I can teach a sensor according to my need. I'll give you a simple raw example. For example, I am using a small ultrasonic sensor, which is supposed to detect the object from a distance of 10 mm, or also let's say from a distance of 100 mm. Tomorrow, I know the size of the component has changed and it has increased, and the sensing distance is reduced to 50. So what I need to do what I need to do is I need to go to the machine, go to the sensor, teach the new parameters to the sensor so that it can work accordingly. But with this IO-Link feature, if I have a connected sensor with the control room to the control room, sitting at my control room, I can change all those parameters. So wherever we have batch processes or where we have processes where we need to change the parameters frequently, all that can be done sitting at a remote location. So that means automatic parameter settings can be done. It is same like what we use. It is nothing new. With the connections and everything are same. There is no new wire, new hardware that is required. Only a single wire which was giving an output is now on the communication bus. So with this, we can do automatic parameter settings. Like I said, if the sensor goes faulty, I have to replace it with the new sensor, and all those parameters which were there in the sensor will automatically get transferred from my control room to the new sensor. That means every time a fault happens with the sensor, I don't need to change or recalibrate the sensor again and again. The same thing can be done. So this is what this technology brings into the sensing world. This is what this technology has added to these sensors. So what all sensors I talked about, whether they were inductive sensors or photoelectric sensors or ultrasonic sensors, even encoders today, radars, LIDARs, RFID systems, all these devices have a IO-Link feature inbuilt into it, which gives us this flexibility of doing so many things sitting remotely. So this is a small SCADA screen where we have a sensor which is supposed to give you a process value. But apart from that, we can also get device data like this, which shows operating hours. So I can calibrate, or I can teach my system, or I can teach inside the system that once the sensor has run for 1000 hours, I have to do a maintenance. So that is the maintenance cycle. Herein, I can teach the parameters of my sensor as per my batch. I can also generate alerts from my sensor if something goes wrong inside the sensor. If a photo sensor has a photodiode inside it, and the light intensity of the photodiode which the receiver is receiving goes down by a certain limit, the sensor will generate a fault. That means either there is accumulation of dust which has happened on the sensor face, or the LED is getting damaged. So with these parameters, I can immediately do maintenance of my device without a breakdown happening. So all these are now available using this technology. So this is what we say are smart sensors for Industry 4.0. All these sensors, they have this inbuilt technology into it. So with this, I would like to end my presentation on smart sensors for Industry 4.0. Thank you so much. Now, if you have any queries or anything you would like to ask, please feel free to ask now. I would like to answer them. I know it was a little, I was not able to share more applications, but since this is a huge product, accumulating in a 45-minute span is a little too small for discussing so many things in it. Please, if you have any queries from anybody, I would be glad to answer.
Thank you, Sudhanshu-ji. I think it's a wonderful session, and the kind of information you have given in a short span of time is remarkable. So certainly you have covered the wide spectrum of the sensors. And as we all understand that sensor is basically the source of the data when we think about implementing smart manufacturing. So we can take at least one or two questions if you have for Sudhanshu before he left. If you can just point out those things, we can have a quick discussion on that.
Good afternoon, sir.
Good afternoon, sir.
Sir, I have a question.
Mm-hmm.
Sir, in railways, we prefer wheels with certain profile. So
Yeah,
can this profile type sensor be used for detecting whether the profile has gone wrong? Because some of the derailment have taken place due to the wrong profile of wheel. So can it be used here?
Yes, sir, exactly. The sensor which I showed you, which was a sensor with a vision inbuilt into it, this one.
Yeah.
This sensor can be used, sir. We can check the profile because, as I said, if it can check the gap, the angle, the stretch, and everything. So this could be the right product for that.
Okay. And my second question is regarding the tank in the water in the tank. We have a lot of watering plates are there in different locations. So can this be installed in that the sensor can be installed in the water tank of coaches so that we know the quantity of water in particular tank?
Yeah, we can do that, sir. See, what we have generally done, not only in railways, it can be done at a lot of other places. Like what you are saying in a water tank, it can be mounted at the top. And based on, because these sensors can generate not only switch output, but also give you analog output. So if you want a continuous monitoring, that is also possible. So what is we teach the empty level inside the tank and the filled level. So between empty to filled, the sensor will generate 4 to 20 milliamperes. So we know how much it is empty or how much it is filled.
Okay. Thank you, sir. Thank you.
Yeah.
Any other question for Sudhanshu? Fine, if no more questions, thank you, Sudhanshu, once again. What I would like to just mention that we already have added a section for you where you can mention your sensing needs actually. So even not today, if you can come across any idea or you already facing some problem with the sensing, please mention those inputs into the FSM Skills website only. And we'll certainly take up a discussion with Sudhanshu, and if required, we can have we can initiate a discussion on that part as well. So please submit your sensing needs actually wherever you are working. If you see there's a need of adding a sensor and then you are still not able to finalize or understand which sensor will be applicable, you can at least give those details. We'll try to help you out on that part. So anything else, Sudhanshu, you are sharing?
No, sir. Fine, sir. Thank you, sir. This was.
Thank you. Wonderful session. Thank you so much. So you can stop sharing, then I will continue with discussion, what I will be initiating.
Sure.
Good. Yeah. So what Sudhanshu has covered in the 45 minutes is certainly the broad spectrum of the sensing that he has gone through. But then we have also have a very nice curated sessions on the basics of the sensing actually. Whatever he has explained is certainly just on the application side, but the basic of the sensing technology, basics of the IO link, all these modules are there into the sensors column in the course actually. So after this session from Sudhanshu, certainly I look forward that he will be going through that content understand little bit sensing in detail, because as we keep talking about the smart manufacturing industry 4.0, everything start from the basic sensing. Rest comes the connectivity and other things later on. Unless you have a right data source for you, you will not be able to utilize the information properly and may not be reaching up to the right decision making based on that data. So that's a wonderful session to start today's discussion. Now I will be continuing on that. What after the sensor actually, once you have the sensors available and selected and finalized, we will be now talking about the connectivity part, and we will be taking this data further actually. So what we will be going to do with this data, that I am going to take up this discussion. So before we come to this is what something I was trying to cover up yesterday, but I will be again starting on the stages in the smart manufacturing basically. So from where to start, you might have understood that certainly the data is the something very important. So we'll be starting from the basic building block for implementation of smart manufacturing is the sensing, implementation of sensing, computing and actuation, because that is where the automation is an important part of this. So though the machines or the systems which already have this kind of a capability inbuilt into them, it's fine. We will be then moving to the next stage. But wherever we don't have this kind of an integrations available, we need to start thinking in that direction. So certainly all the legacy machines or the conventional systems where you may not be having the controllers or the sensors available as it is, but depending on the criticality of the application or the importance of the equipment, you can think about which parameter is most important and what kind of sensors can be added to that. And post that, we will be talking about the connectivity. That is the second stage of implementation of the smart manufacturing. Once you have the first stage accomplished actually, then we will be thinking about the connectivity, because the data that is being captured at the site of sensing is to be further utilized somewhere else. Certainly it will be utilized in decision making then and there itself to some extent, but that is not what we are just confining in industry 4.0. We will be looking forward for a much better utilization of that data beyond the immediate action that will happen in the machine. So these two stages, we normally call them in a prerequisite for the smart manufacturing implementation, or I should say the industry 4.0 implementation. Because without these two, we can't talk about any of the services that are being developed in the smart manufacturing. So if it is already available, most of the time we have a connected machines. Most of the time we have these advanced machines where you already have a sensors and computers inbuilt into them. And I'm sure that those who are just sharing their experience and starting their journey for industry 4.0, they are basically starting these prerequisite stages actually. They have already accomplished this prerequisite part. They have established the connectivity with the various machines, various systems, now able to get the data. So that is the most important part to understand. Now, post that, once we have done the connectivity, once we are getting a data to us, what we are going to do with that. So that is how the next stage of implementation is to bring out the visibility. What is happening inside the process? What is happening inside the machine? So once you have that data, you will start understanding that data. You may be able to project that data and able to utilize that data to understand what is happening in the system. So once you accomplish that, the visibility part, that's what the visualization part at least. So after that, we will be looking forward for the transparency. Now we will be sharing this information to the different stakeholders, let them understand why is it happening actually, what is the source of this good or bad outcome, what is coming out of the system. So that is the next level of implementation. We call it transparency. So whenever we implement these modules or these stages in the organization, slowly we will be moving towards the implementation of the industry 4.0 or what we call smart manufacturing. Now, once we build this transparency, then we will be talking about the building of the predictive capacity in the organization. And that's again a very important part when we keep talking about the predictive maintenance, prescriptive maintenance, and then proactive approach that I was just discussing yesterday. Now we will be preparing the organization for such kind of an incidents in advance. So that kind of predictive capacity can be built through the implementation of these technologies. So now, after you created that data, once you have that data into the system, these are all the services that will build up on the top of that data and the information that is being generated. So then you will be building a predictive capacity in the organization. It means that you will be preparing the organization for such incidents to happen before they actually happen. So that is what the next stage. And certainly later part we will be implementing for the adaptability part. So adaptability also I have discussed the adaptation process I have discussed yesterday. What we want to do, finally, we want the action to happen actually. So the corrective action should be implemented and the system should be self-adapt to the changes actually. So that is what, whether it's an optimization, whether it is to be a corrective actions to be taken. So we are looking forward for such kind of an autonomous decision making to happen at the system end, and they will be finally implemented. That is what we are looking at right now at the higher stage of the industry 4.0 implementation. So as we go along these stages, then certainly we will be building these capabilities in the organization to reach out to the industry 4.0 implementations. We start with the basic building blocks, and that is what most of the industries are at right now. They start at least establishing the connectivity, bringing out the data, and I'm happy that most of them are able to bring out to the visualization level. Now, post that, whatever is required to build the transparency, predictive capacity, and adaptability is the next stage of implementation. So what kind of services you will be able to build on top of that data is more important to reach out to the last stage of the smart manufacturing implementation. So as a part of this, what Sudhanshu has shared, I'm just adding few slides to that when we talk about the smart sensors actually. So earlier, you know that the sensors, we are just getting an analog value out of the sensors, and what Sudhanshu was mentioning about the IO link, because now you are placing in a controller and now you are placing in a communication to that, and over a data bus, you will be sending much more information than just a parameter value. So that is where the role of the smart sensing come into picture. So these smart sensors are very important in getting a digital insight into what is happening actually. And these are the source of the real-time information for the managers, allowing them or arming them to get the information about the inventory, the status of the machinery, or certainly any kind of an information which is important to know about in the real time. They are trying to give you the visibility across the whole supply chain, and then they are the basic fuel for the analytics, because without data you can't do any analytics, you can't analyze the data. And then all sort of technologies we are talking today, they are basically relying on the huge data that should be available to analyze actually. And by using that analytics, you will be in a better situation to anticipate the demand, optimizing certain parameters, and then you will be able to take a high value decision making in the manufacturing. So that is the idea of getting the smart sensor, not just a parameter, but you will be getting much more additional. And many times the sensors are also now capable of doing some kind of a basic analytics onto that themselves also. So if you look into the future of the sensing and what are the recent developments today, actually, it's not just a sensor. You need to build about a lot of technologies at the back end to utilize that information coming out from the sensors. So when we talk about the recent development in the smart sensors, certainly the basic parameter that you will be capturing from the sensor is the one important part of this. But then you need to have a lot of analytics tool at the back, because what you are going to do with this data means who is going to analyze this data. So that is the important part. To extract the meaningful insight from the sensor data that you are getting actually, you need to have an access to the analytics tool, and that is how you will be able to analyze all the sensor data coming to you and making a meaningful inference out of that data. How you are going to handle this data is, see, just placing a sensor will again not serve the purpose actually, unless you have a backend system to handle and manage this data. That is where the role of the big data is coming in. People are talking about the multiple type of the data, because vision data is also there, the sound signals are also there, vibration data is also there. So there are a lot of type of data that is coming, and then how you will manage this big data, what kind of platform is required to handle this kind of a data. So understanding and know-how and the capability to handle this kind of data is also required. So sensing, implementing smart sensing, just start with a basic sensor, but then you require a large number of technologies at the back end to really utilize the sensor information. Then you should also have a real-time processing capability. So when you should have a tools basically which will enable the processing to be happen in the real. So the kind of processing power that is required basically, so that in the real time you will be able to get a decision or the action can be taken based on the sensor inputs. Otherwise, most of the time we log the data. That is what is happening. Whenever we install the technology, we put the sensor, we put the servers, we put the connectivity, and most of the time we keep on logging the data. So now this log of the data is certainly useful when you want to dig out what happened actually in the past. So instead of doing that, we would like to build up a system which will be more responsive, and then you will be able to get the information in the real time, and the decision can also happen in the real time. So sometimes they are based on the human decision making system, or sometimes you would like to implement the autonomous decision making. And certainly there are new algorithms for the energy saving on the sensors. We are looking forward for the analytics and what are the new analytics can be done on this sensor data. So there are new developments happening in terms of the algorithms on that, so that we will be able to prescribe much better action for them. So these are the additional developments on top of that, what the smart sensing being discussed, and we all understand that the smart sensing is just a start of this understanding and the knowledge, and then we will be requiring additional technologies to handle this data. So this is just a quick update on what Sudhanshu has shared. So to make use of this sensor data, we need to build up a connectivity in the organization. So I am sure that those who have taken up this activity and then tried out their hands-on in implementing this connectivity part, there's a lot to know and understand whenever you're talking about the connectivity and the scalability part actually. Building a connectivity with few machines is not that difficult. You can easily do that, you can implement that. But when it comes to the implementation in a bigger organization, large number of machines, large number of automation systems, the field level implementations, the control level implementation, you need to understand the different links for the communication actually. So that is where the challenges comes in terms of understanding and implementing the industrial IoT network. And then if you see the major levels that are being shown over here, that we'll start the connectivity to build up from the field level. So you will be having a devices, machines, equipments, individual sensors are also capable of pushing the data these days. You may not be required to hook up them to any of the PLC. You can directly pull the data from the sensors and take out to the control level actually. So that is what you can see here. So you have field level devices, which will be the source of the information, source of the data, taken to the control level so that the data will be analyzed and certain control action will be taken up. They may be used to visualize that information on the machine also. And then the information will be shared at the enterprise level for a bigger decision making. And then you will be sharing across the enterprise also with the help of the connectivity with the cloud. So that is how the different layer of the communication need to be inbuilt. And the most challenging part here is getting the data from the heterogeneous devices actually. So whenever you try to implement the industrial IoT, the challenges start from there itself, because there are multiple manufacturers, multiple protocols you are supposed to handle. So that let me just brief you in that part also. So this was the problem we were discussing yesterday, that we would like to convert a machine into a smart machine, and then we will be talking about the different sensors to be integrated into the machine. But after that, how you will be exchanging the data with the machines and the IIoT. So that is how I will be explaining this block further. To implement the connectivity to this machine, certainly we would like to place multiple sensor onto this machine. So whatever Sudhanshu has explained, let me just carry that discussion. So we have converted this equipment, which is a legacy machine, in our central workshop with the integration of the multiple sensors. So the first idea for implementing on any of the legacy machine, we have to think about the machine, the need of those critical parameters. And then we have to identify a right sensor for the application. So in this case, as you all understand, that we need to measure the feed, depth of cut, and these are all displacement. So we need to identify a right displacement sensor for the measurement of the depth of cut, measurement of the feed rate. So if you can see along the bed of the lathe machine, we have placed this feed displacement sensor. Across the carriage, we have placed the sensor for measuring the depth of cut over here. And then when you have these kind of sensors being placed onto the machine, you need to have some kind of a controller to capture that data. So we have used a small controller with an HMI also inbuilt into that. So all the analog sensors are being interfaced to that. We have also some of the proximity sensors to sense the RPM of the spindle, and then sensing the presence of a key for tightening of the chuck. So as a safety measure, we have integrated that part. And then the vibration sensors, how you will be taking out that vibration sensor information, and certain IOs will be there. We also added an RFID access to the machine. So idea is that once you have these kinds of sensors and the devices, you need to connect to the controller. That is what has been explained. And from there, now you will be taking the data for that. So then you'll see that the connectivity has been established from this machine, and which will be having this sensor. So machine level connectivity has been implemented. And from there, you will be taking the data from field level to the control level. That is, your controller will be there. And then from there, we will be taking to the manufacturing execution system and the ERP systems. So that is where the connectivity of the lathe machine till the enterprise level is very important. What I was just showing, the multiple layers of the. So we have done this project, and we have already exercised the implementation of the concept of the IIoT in this case. What all tools are required to implement this is very important to understand. So that is what and then certainly you can build up these kind of smart applications for the once you have a data for the visualization and for monitoring purpose here. So what I will suggest, I will try to utilize the rest of the time in first session itself to give a quick live demonstration. So my colleague, Mr. Arun Kumar, has joined from the FSM lab. And just want to give you at least the practical hands-on on what we are talking about. And then certainly the theoretical part will continue discussion in the subsequent sessions. So I will stop the sharing over here. I will request Arun to please be available from the FSM lab and then share the connectivity part with the sensors. Over to you, Arun.
Hello, thank you, sir. Good afternoon, everyone. I am Arun, and I'll start this session by introducing you with the components of PLC training
Arun,
kit.
we can't see you right now. Can we see you where you are right now? So you will be explaining those systems, so then we can see it.
Yes, sir. Sir, is the screen visible now?
Yes, Arun, we can see that.
Okay, so I'll start by introducing the components of this kit. So this is the smart kit which we have for the demonstration purpose. And the first component is SMPS, that is switched mode power supply. So it converts 230 volt AC into 24 volt DC. All the devices that are used in this kit use 24 volt DC input. So this device provides that input to the other devices. Then the next component is PLC. This is the brain and this is the controlling device of this kit. All the programming is being done in this PLC itself. It has embedded DI and DOs. It's a Rockwell PLC in this kit. Then there are different other kits which have other controllers like Siemens and Schneider, etc. Then this is analog input and analog output. Then this is Ethernet switch. It's a managed switch. So the difference between a managed switch and unmanaged switch is that unmanaged switch only communicates the devices with each other, and it does not provide any security in that communication. Whereas this managed switch provides the this security part. So you can configure the port depending on the device of which was connected on that port. Then this is IoT gateway, which Jha sir was just mentioning in the previous session. And this is the IO-Link master. So this IO-Link master communicates with all the sensors that is connected in this kit. And this IO-Link provides the data to the PLC. So along with the digital and analog data, it also provides the diagnostic data of those sensors. Then this is the mechanism kit which we have. So all the sensors are being embedded in this kit. So this is the RFID station. It has a RFID controller. This RFID is also communicating on IO-Link. So this RFID communicates the data to IO-Link master, and then this IO-Link master communicates to the PLC. So I don't have to configure anything in the RFID. I just have to connect this RFID to the IO-Link master, and I will get the data. So this can read and write the data of the RFID tag. Then the next station has this ultrasonic sensor. So as Sudhanshu sir has already mentioned that this can be used to measure the height of the object. So we are using for that purpose only. Then the next station is have this USB camera that is used to calculate the diameter of the circle of this part that is present on this station. Then the next station is solenoid station. It is used to demonstrate the stamping operation. And then we have a servo motor and servo drive to rotate this disc. This disc has three parts which will be rotating, and different operations will be performed on these parts. Now I will be explaining the communication, the steps to communicate this IO-Link master with the PLC. So as we are using Rockwell PLC, we will be using the software for Rockwell, that is a Studio 5000. So this IO-Link master is communicating on Ethernet IP, and our PLC is also communicating on that protocol. So I'll just create a new project, and this is the part number of my PLC. I'll just give a name of my project. So if I am communicating any device on Ethernet IP, I need an EDS file of that device to communicate with the controller. If it is communicating on Profinet, then we need a GSDML file to install in the controller. So to communicate this PLC with the IO-Link master, I need to install the ADS file of that IO-Link master, and you can get the ADS file on the website or from the datasheet of that sensor. So this is the part number of my IO-Link master. I'll just add this ADS. And now you can add the device in your project. So this is the IO-Link master, and I'll add this to the project. Here I have to mention the IP address of IO-Link master. And here you can add these input and output bytes depending on the requirement. If you are using a signed integer, you can use this int data type, or if you are using integer, then you can use int data type. So after adding this ADS and this device into your project, it will create some bytes for the input and output. So these are the bytes. So in IOL colon I, you will get the input from IO-Link master, and you can also give output to that IO-Link master using this IOLO. So I have already downloaded one project in the PLC. I will just show you that. So this is the project, and these are the input bytes of IO-Link master. So these are the RFID data which IO-Link is communicating with the PLC. These are the input bytes, and these are the output bytes on which I can write. So these are the bytes which is used to write on the RFID tag that is present on the part. So I'll just show you by rotating you the disk that how this RFID controller is reading the data from the RFID tag. So as I have given a position 1, it has rotated to the RFID station. And this is the RFID tag value of this part that is there in front of the RFID station. Now I'll again rotate the disk. It has again rotated. And now these are the RFID bytes of that RFID tag. So this is the PLC communication with IO-Link master. Now I'll show you how to send the data from this PLC on OPCUA or from this IO-Link master. So you can also send the data from IO-Link master directly through OPCUA. So this is the CAP server platform. This is used to collect the data from your hardware controller, and then you can send this data to any IoT platform. So you just have to create channel. So these are Allen Bradley for Rockwell PLC. You can use these Ethernet channels also. And for OPCUA, you just have to add OPCUA client. OPCUA client. So I'll add this IO-Link master directly to this CAP server platform. And you can see the tags. So I have created a channel with name IOL, and now I'll add the device. So now I'll import the items, that is, it will this CAPware will import the tags from this IO-Link master. So this is communicating, and I'm getting these tags. I have connected the these sensors RFID and this ultrasonic sensor on port 3 and port 6. So I'll just add status of port 3 and port 6. And for your reference, I will also add the status of port 1 and port 2. So we will get to see the difference between the status of these 4 ports if I have connected any sensor on some port, or if I have not connected any sensor. And these are the SIO input and SIO output, which Sudhanshu sir was mentioning in his session. Okay, I'll just show you the data on this CAP server platform, and from this CAP server platform, we can send the data to different IoT platforms like ThingWorks or through MQTT protocol also. Okay, so these are the tags which I have added. So status for port 1 and port 2 on which I have not connected any sensor. The status is initialized. We have to initialize by connecting some sensor on that port. And for port 6, it is in operation mode, port 6 and port 3. And this is the uptime of port 6. So I am getting the values of all the tags that is present on IO-Link master. Similarly, I can also add the PLC and I can get the tags of this IO-Link master through the PLC communication also. So I'll just show you the dashboard for this this kit, and when I rotate the kit, you will see this tag value, height and diameter parameters changing. So this is the IoT platform. You can access this dashboard from anywhere. So I'll just rotate the disk. And now you can see the data changing from this RFID for this RFID tag and height of the product.
Thank you, Arun. Anything else you are showing?
No, sir, I think.
Okay. Thanks for this quick glance on the kind of technologies being involved in getting the data from the basic sensor and how we will be using that sensor data. So I think the idea behind this 15 minutes visit to the lab and then give you an idea about the different platforms being involved is just to understand the kind of technology understanding required to bring out the data from the systems and finally taking it to the IIoT platform and creating a visualization, because till now we have just created the visualization. So we'll subsequently discuss in the coming sessions how these implementations happens, and certainly within the time available to us, I will be only giving you the overview of the technologies. And normally when we conduct the detailed in-depth sessions, we will be taking all the participants to do these hands-on exercises, because sometimes it is very important to understand how these things will be implemented. So for the first session, we will be stopping over here only, and let's have a quick tea break, and then we will be joining again at 4:20 for the next session on smart machines. Thank you so much.
On the smart managed machine concepts and technologies. A brief about Mr. Pankaj. Pankaj Aswal is working as Regional Business Lead Architecture and Software Business Unit of North India. In this role, he is responsible for driving architecture and software business initiative across OEMs, end users, EPCs through partner ecosystem in North India. Pankaj has over 13 years of experience in Rockwell Automation. Before taking up role of business lead, Pankaj Aswal has worked as key account manager for consumer packaged good and life science industry. As key account manager, he has driven digitalization initiatives for customers like Nestle, PepsiCo, J&J, Unilever, ITC, and Mankind Pharma. Pankaj has completed MBA from Great Lakes Institute of Management, Chennai, with specialization in operations and finance. Welcome, Mr. Pankaj Aswal. The floor is yours, sir.
Thank you, Naman, for inviting me for this session, and a very warm good afternoon to everyone. I'll just share my screen, Naman. Let me know once it is visible.
Sure, sir. Your screen is visible, sir.
Great. And I'm audible?
Yes, sir.
Great. Okay. Good afternoon, everyone. Again, my name is Pankaj Aswal, and I handle software control business for Rockwell Automation, North India. And today our topic for discussion is smart machine, how we can build smart machine, and so that machine is able to provide greater value than its sum to the organization, right? So we'll go through the basic modules of a smart machine, what should be incorporated into the machine. Then we'll also look at the software side of things, because software is a major component in building smart machines, right? So to begin with, some of the driver for a digital transformation into any organization. The first one is time to market. With the help of digital transformation initiatives, companies are able to reduce their time to market, whether it is a company like railways, where you have your own setup for producing components. So you can introduce those faster to the market by doing the prototyping in a digital world with the help of digital twin technology. And then also ensuring that whatever is produced on the machine, that is produced in the minimum cycle time possible. Then productivity. Digital transformation benefits also lead to massive improvements in productivity, right? So just by capturing the OEE, which is a very popular term for plants with a lot of machinery, you can save easily 4 to 5% annually, right, in terms of OEE. And that leads to substantial improvement in productivity of customers. Then with the help of digital transformation, supply chain can be optimized, inventory days can be reduced, and this results in better planning and forecasting of your demand, right? And then regulatory, of course, digital transformation can also comply manufacturing operations with the various compliances. For example, in pharmaceutical, they have to comply with the FDA norms, whether set by India or US or Europe. So with the help of digital technologies, they are able to do so. Or for example, environmental norms. So emission monitoring or ETP plant, those kind of things can also be automated, and compliance can be achieved with the help of digital transformation initiatives. So a basic question can come, why anyone should build smart machines, right? So the benefit of building a smart machine are categorized into 4 buckets over here. The first one is added value. It provides added value to the organization, right? Either by the advanced process control or with the help of condition monitoring. Advanced process control, one typical example will be to reduce giveaway. Every industry has got some giveaway, right? The component that is produced or product that is produced by a company, whatever is the minimum requirement of the raw material required to produce that product, generally it is slightly above that, right? So how that giveaway can be reduced, that is possible with the help of advanced process control. For example, in a food industry, that milk powder that comes into the market, the moisture is a very critical parameter there, right? So in case the moisture is high, the powder quality will be less, right? In case moisture is low, the company is selling more milk into the market, right? So with the help of advanced process control, customer can optimize the amount of quality required to ensure that product goes to market within the compliance, right? Then with the help of condition monitoring, customer can switch from time-based maintenance to condition-based maintenance. Right now, there is a periodic schedule at which maintenance is done. With the help of condition monitoring, customers can shift to condition-based maintenance, where based on the event, they do the maintenance of the machine. It saves in time and reduces the planned downtime requirements of the machine. Then it also helps to reduce cost. For example, there is a new equipment required in the plant. So there will be a lot of prototyping investment required, right? So with the help of digital twin technology, the prototype can be built in a digital environment. And before taking that to physical world, all the functionalities can be assured into the digital twin model. And that actually reduces the cost to bring the final product to the market, right? And this revenue stream benefit is not particularly for end users like railways, but OEM side, there are various business models like selling compressors on OPEX model, where OEMs charge end user for the amount of running hours of the equipment. Those kind of revenue streams are also possible with the help of smart machine technologies. Then also it also leads to IP protection, which is a big topic today. Cyber security. Many of these machines, they have vulnerability to the IP protection, right? So any vendor can come with a mischievous intent, and they can steal the IP of machine. So with the help of digital technologies, companies can ensure that they build defense in depth concepts into the basic machinery, so that their IP property is that stays with them. So it reduces risk in that way. right? Some of the common challenges we hear from market when we talk to customers regarding digital transformation is that customers don't have time to execute digital transformation projects, or their machines they feel are already smart, or their IT department won't give them permission, right? But sooner or later, everybody is going for this kind of initiatives, right? And IT department, if they won't give access, but definitely CEO of company for improving the COGS or improving the turnover profitability, these initiatives are must. So what the question may come that what is a smart machine, right? Every company already has automation inbuilt into the machines which they are buying from various equipment manufacturers. So that is true to a large extent that whatever machinery comes into any plant these days that has got a PLC, that has got a human machine interface, that has got a variable frequency drive, for example, then what do we call a smart machine, right? So all these smart equipment which are there installed on the machine, they are generating real-time data already, right? And how companies are utilizing this real-time data to improve the operation of the machine and then of the entire production process. So that is what constitutes the smart machine. If we are able to secure this real-time data and give context to it, right? So we have basic parameter like running time, temperature, voltage of machinery already released by various sensors to the PLC, PLC to HMI, right? If we can give some context to that, turn that data into relevant information like OE or energy produced consumed per product, right? So this kind of contextualization will be relevant to companies for doing improvement, right? And then on top of it, if we can do further built analytics right onto this whether machine will fail in last 10 hours. So this prediction will also come based on the historical fault history that is available in the local machine HMI, right? And then based on this data stored, we can create more efficient workflows for the machine so that it performs at the highest optimal level. So that basically constitutes the smart machine. How we are able to turn real-time data into a contextualized report to analytics to optimizing the workflows, right? And if I talk about basic technologies for smart machine, the first one will be integrated safety, right? So generally a saying goes like productivity is inversely proportional to the safety system, but that's not true. The higher the safety on the machine, the more productive the machine will be. That has been our experience, and as per the studies done by global agencies as well. So integrated safety is absolutely a must building block for building a smart machine. Then smart sensing. With the help of technologies like IO-Link, it is possible to take the sensor onto a network and collect relevant diagnostic information from these sensors so as to increase the uptime of the machine and also improve the process workflows. Then smart motor control. So you may have VFDs, soft starters built into the machine, but how you leverage the information which is coming out of the smart motor control systems. So that also constitutes a building block for smart machine. And then once you have all this, on top of it, we have IoT platforms, so which ensures that machine provides the value beyond its own sum, right? So this machine may be producing one component or doing one task of the operation, but with the help of smart machine, it can provide greater value to the entire organization than its sum. If I talk about first one, the integrated safety. So this is a graphic for a plant, right? So this plant has a machine safety components built into the machines. So as you can see that the diagnostic available is of advanced level. Like for the light curtain, the margin is low and cleaning is required. That kind of prompts are available. Or the switch is damaged. So switch itself is giving this alarm that switch is damaged. Or light curtain, how many trips have been there for the one day, right? Or there is a misalignment on the guard door. In case this one is not a network safety system, it is very difficult to troubleshoot this in real time, right? With the help of smart safety systems, we get all the diagnostic into a controller, and from there we can do various kind of analytics on top of it, right? But these kind of dashboards are possible if the machines have integrated safety. one more example. So this one is real-time risk estimator. So many companies, they do safety risk assessment for machines. So based on that assessment, so there is a exposure which comes, this is a static data, like guard door 1, the access should be less than 1 per month. Guard door 2, access should be less than 1 per month. For some places, it is greater than 1 per shift. So frequency of operation is really high. This one is coming from the field sensors, current month exposure, like this red one. The light curtain one, the frequency should have been 1 per month, but currently month exposure is 44. So there is a high risk that there will be an accident onto this light curtain one. Actually train the operator and ask them why they are going so much to this particular section of the plant. Or this one, e-stop. It is greater than 1 per shift, but still current month exposure is 1836, right? To 6-month average is 8667. And if you see the second one, e-stop 2, the exposure, anticipated exposure is greater than 1 per shift, but current month exposure is 0. So that means system is the production supervisor or the EHS manager of the company should look why this system is bypassed. Right. Second component is smart sensing. So with the help of IO-Link technology, he can take sensors onto a IO-Link network, right? And with the help of that network, sensor will themselves give the diagnostic information through a network, like parts count, or if the sensor is overheated, or there is a setup issue on the sensor. All those information will be available with the help of IO-Link technology, right? In fact, if there are suppose multiple components produced on the same machine, the recipe can it sir, or things like photo eye, which does not require a separate teaching every time for different products. So very popular technology these days for sensor technology, and this can directly be integrated into the controller of the machine, and all the diagnostic information is available from the sensor onto the local HMI or to the higher IoT platforms. It also gives timestamp data and diagnostic about the sensor health to the control system. And then multiple profiles can be stored inside the sensor. For example, photo eye. For different kind of packaging or different teaching is not required for photo eye. A recipe can be downloaded from the HMI to the machine, and that reduces the product change over time. Right? IO-Link is a worldwide open standard. It is a peer-to-peer serial communication product, and it is forward and backward compatible with the standard sensors that come into the market, as it uses the same cables as the standard sensors, and this can transmit data from IO-Link and further through Ethernet IP to the IoT platforms. So these are the 3 use cases for smart sensing. Predictive maintenance. It is able to preempt that there is a low margin, and based on this alert, operator can take action, or they can store the recipes, change sensor configuration on the fly, right? So that they need not do the manual adjustment after every patch. Replacement, it takes a lot of time to first of all find out where the problem lies. In case of a smart sensor, it will automatically prompt that I am faulty, and the troubleshooting time will be very less with the help of this kind of technology. If I talk about smart motor control, so if variable frequency drives, soft starters, or smart overload relays are onto network, then we get not less than 50-60 parameters per motor onto the our SCADA or HMI, whatever you might be using. It also gives you things like underload condition or jamming condition, time to trip, high vibration onto any pump. So all this diagnostic is available with the help of smart motor control. And you may be already using VFDs, soft starter, into your operations. Condition monitoring is something which is really becoming popular these days. So where we track the vibration of the system through eddy current probes, And this system is our central controller, and it gives the alerts onto the local HMI. You don't need a separate offline analysis for predicting when it will fail, right? So this can be done in real time. So we have seen the building blocks for the basic machinery. On top of it, software is really the main secret sauce of building a smart machine. So we'll be talking about some of the software as well as giving 5 minutes. But the whole, I would say, smart machine concept, if those sensors are already in place, it becomes very easy to implement the smart machine concept into it. So the first concept we'll talk about is digital twin, and we'll also show you demonstration for this digital twin. So what is a digital twin? It is basically a digital representation or a digital replica of a physical asset. So how a machine behaves in a real environment, I create a similar twin of that machine into the digital environment. And in case I need to do some modification onto the machine, first of all, I'll do the modification in the digital twin of the machine so that I don't incur investments onto the physical prototype. I do my modification into the virtual world, and in case it works fine, then I implement it that really reduces my time to market, as well as it ensures that first time right, which is a major KPI for many companies into lean these days. So what are the use cases for digital? We can do the real-time throughput analysis of a line. We can do machine prototyping. We can do virtual commissioning without actually commissioning the machine in a physical environment. Design machine, we can simultaneously do the virtual commissioning. So when finally we deploy the machine on site, the errors are very less or no error at all, right? And this can also be used for operator training systems. This is typically the plan for deployment of any project, right? We design, manufacture, and commission, right? And control testing goes on when we are commissioning the machine. But in reality, design and manufacture takes longer time, and because of which commissioning is delayed. And we finally overrun the deadline required to complete a project. With the help of digital twin system, we can actually start the control testing as well as operator training while we are manufacturing the machine itself, right? So that we are able to finish the project well within time. So how we do it? We basically merge your drawings, the 3D drawings, with the PLC logic, right? And we then have various conditions of kinetics and physical motion on top of it, so that we can have actually an animated which will behave as if you're doing work on the actual machine in the field. So coming to the next topic is IoT platform. So there are two approaches to digitalization. One is the application for a particular use case. Like if I want to measure OE of a machine, I built a separate software for that machine. Second approach is of a platform. Just like you have Android onto your phone or iOS, or you have Windows onto your laptops. Similarly, for IoT, there is a concept of IoT platform, which is able to connect to any kind of device on the shop floor. Then this IoT platform, we can build apps as per the requirement. Building apps on top of it results in scalable deployment as well as reliable document, because the services used are common for all the apps, whether it is OE quality monitoring or for any other use case, right? I have the basic info on the IoT, and on top of it, I built various apps. And this is one of the snapshot. We'll also show you demonstration. So this is the IoT platform. The data coming from the various machines onto various plants. So on the left-hand side, we have mapped the various factories across the globe, right? As you can see, somebody who is sitting at a leadership level, or a plant manager wants to see performance of the plant, they can click their particular plant, like here Cincinnati plant is clicked, and they can see the production KPIs of that particular plant. And if plant manager wants to any other plant, they can also do that just to see how the plant is performing compared to a benchmark. That is possible with the help of IoT platform. The second concept is on augmented reality, where we superimpose digital data onto the physical world. So just to give you a example of this, we generally mentally understand the GPS images, and then we, based on our own conditioning, the action, maybe right turn, left turn, based on the GPS signal. But that is a little tricky in the real world environment when we are operating the machines. So what if we are able to get all the digital signal right in front of our eyes, in front of the screen, right? I have to turn right. I can physically see onto the road in front of me. So this is possible using the augmented reality technology. And there are multiple use cases in manufacturing environment. Like when somebody is doing the lockout tagout of the machine, they can get instructions right in front of the machine. Or somebody wants to troubleshoot the machine, they can get fault history of the machine from SAP or from the PL shop floor. These are the various industrial applications. As you can see, manufacturing operation is one of the top 2 in terms of use cases for augmented reality. Other is the service. I will pause here. Just one more concept, defensive depth. So when we are implementing smart machine technology into the plant, we have to ensure that we follow the cyber security norms, right? So we have something called defense in depth, which we have collaboration with Cisco, and all our system comply to this. So what we say is that there should be security implementation at all the levels into any smart machine implementation. At the device level, this is the basic machine level. Here we are disabling the unused port and ensuring that the right person is able to log into the system level. We ensure that there is role-based login and right security measures are implemented. Then at network level, the switches are configured so that unauthorized access is prevented. And so whenever we implement any smart machine implementation, we ensure that cyber security practices are followed into that. With this, I would like to now hand over this to Abhirat, who will take us through the IoT platform as well as augmented reality demonstration. Abhirat, are you on the call?
Hello. Yeah. Thanks, Pankaj. Just give me a second.
Yeah.
Recording in progress.
I was just trying to. Okay, that seems to be a little tricky. Okay. So I just share my screen.
Pankaj, you can stop sharing your screen, then only we can see his screen.
Are you able to see the screen?
No, Pankaj has to stop sharing his screen, then we can see it. Yeah, now we can see.
Okay, so this is an example for the smart connected products, right? So here I have taken an example of smart connected machines. Basically, these are tractors, and all these tractors are connected. So I can see from clicking on each of the tractors, what is the RPM at which each of these machines are running, or what is the location of each of this machine. And if you click on the specifications, we get to see what are the in detailed specification of these tractors. So to go a little bit deep into why we are collecting these kind of data, we can actually select each of the product and see different plots and see how they have been performing. As in case of this tractor, we can see how and where they have gone, what is the route that particular tractor has taken. We can see the pressure readings, how the pressure of the machine has been dropping with the respect to warning levels and critical levels. when the pressure is dropping below this kind of critical level, the platform will give us alerts telling that, okay, there is something required. So you can see here corrective maintenance is required because it has gone below. It is hydraulic pressure. Same way, we can monitor different parameters. You can see the speed going on here, how the pattern of speed was, how was RPM, how is the vibration of the machine going in x-axis, y-axis, and the average vibration, and other outside conditions, how it has been, like engine temperature as well as ground temperature, how is it correlated. So by plotting these, we get a lot of understanding of how in detail these kind of machines are working in the site. And on top of this, we are able to apply analytics. So when I say analytics, I am switching to another use case now to show you a bit on how the analytics works. So this is something like a smart connected pump. So you can see here, there are multiple pumps that are sending data into the IoT platform. So this is a one particular pump. It's an auxiliary mesh pump. There is some, we are actually predicting how much discharge this pump is able to do. So if you see the details of that one particular pump, you can see we are monitoring the vibration. By monitoring the vibration, we will be able to do the anomaly detection also whenever these trends go out of the range. We can see other analytics, streaming analytics, which is actually mean, max, median, and then the standard deviations that the machine are having from the defined analytics. We can also do SPC charts here, X bar R chart. These are statistical process control chart, which gives a very clear idea on what kind of statistics are we talking about. And on the predictive analytics side, we can see here, this is the kind of model that we are able to build, and what is the kind of quality of the ML model that we have already built. So we have some of the parameters for the ML models here, like correlation and R square, etc. And this is the model which is giving the prediction on what is the kind of discharge that each of this pump would give. And whenever there is a discharge which is going below the certain level, we will be getting an alert. And this alert can be sent through emails or as text messages. We can integrate it basically into other systems also. So this is a demo on how smart connected products work along with analytics. Shall we move to the next demo?
Yes, I think for sure.
Okay, so I was actually trying to give a live demo, but the Zoom app in my mobile
Yeah, is there any questions so far from the Is there any question from the participants?
Okay. So I was trying to do the augmented reality live demo, but unfortunately I am not that well conversant on Zoom in my mobile app. So I will try to share the videos and give you an example. Right. Okay. So here you can see this is a tablet. So our AR offerings support other devices such as HoloLens, RealWear, and even Magic Leap also. That's a new headset that has been coming out for the AR area. So this is a kind of a sales and marketing use case that we have. So if you have a product, how we can enhance the experience on that by giving instructions like this: what are the areas that you are not supposed to do, or what are the live data monitoring that we can do, or to identify different parts. Where is the motor, where is the track, where is the switch, where is the curve. So these kind of use cases can be covered using sales and marketing use cases for augmented reality. And then in part of improving training, so you can see here, this is the machine that this particular worker is actually assembling. And using a HoloLens, we are giving all the required information and different steps that he has to perform to assemble this particular machine. So you can see here, it shows him the sequences in which the machine has to be worked out. It will also show him what are the tools that has to be done, which tool has to be used to what limit, what are the next steps. It also shows the pictures and other supporting documents that will give him confidence to do the work. We can show them the internal working of machines. So many times these machines are not opened up fully and they might not have an understanding how it works internally. So we can give such kind of graphics which gives a clear idea on what is how is it actually working. So there are these kind of internal workings that we can show. And ultimately, all this improves the confidence that any worker is having to do some worker or do an SOP on any machines. Also, this can act as a guiding app for the OEMs when they are providing it to their end customers. Any questions? Okay, so one of the last use cases is in field services. So this is a tablet view that we are seeing here. So let's say our platform can actually identify the machine based on the boundary of that particular machine. So you can see this is the boundary that we are tracking. And as soon as you will see that the tab is placed onto the machine, it understands the machine, right? So it is already telling you that there is an alert. So this alert is generated through IoT platform. So IoT platform passes on that information to the augmented reality app. And that's how we are figuring out, okay, this is the specific problem in the machine, right? So this is a problem that has been identified by the IoT platform. So there is something wrong with this particular gear in that machine, and there is an alert for that. And how do we rectify this? So we have to actually check and open this up and check. Before opening up the machine, there are some checklists that we have to follow. For example, you have to see if the blower is very hot, if this part is movable, ensure that some parameters like pressure is within the level before opening the machine, right? And maybe we can also show some areas that are hazardous and people are not supposed to enter in. So these improve the safety of the workers who are dealing with these machines, as well as it takes him through the correct steps on how to operate on the machine. So once those checklists are complete, next we will show what are the process in which he has to take out each part, how to deassemble the whole machine. So now here we see the deassembling sequence, which part by part he has to open up the whole machine. And once the machine has been expanded or exploded, we can replace that particular gear. And of course, once that particular gear is being replaced, we will also show the reassembling sequence, which would be something like this. So this is the use case for field services. We can also show, as we saw in the earlier use case, we can also show what are the parts and where does each of the other parts lie. And we do the online monitoring too. So yeah, that's the demo from my side. Any questions? Okay, thanks. And back to you, Pankaj.
Thanks, Abir. Is there any question from the participant? So I see one question on which software. So this demonstration was for Foria Studio software. Okay, so
So in fact,
now I
we
would
had
like to invite Vijay Bhatt to
yeah,
give you demonstration of IO-Link technology.
Pardon?
Yeah, Dr. Jha, please.
No, I was just mentioning that we had a detailed session on AR on Monday. That is what I was just trying to explain from PTC. So we will even also take you through the hands-on experience, how to create these kind of an AR. So from our lab, we will at least demonstrate that also. So certainly what you have seen being shared by Abhirat are wonderful applications of AR, but we'll take you a little deeper into how to implement the AR when we have a dedicated session on that.
Sir, I also have my colleague Vijay team to the IO-Link sensor technology as well as digital twin using Emulate 3D software. Vijay, are you on the call?
Yeah, Pankaj, I'm on the call. So shall I share my screen?
Yeah, Vijay, over to you. Yeah.
Okay. Okay, so is it visible? Screen is visible?
Yeah, Vijay, it's still coming. So we are waiting for that.
Okay, okay. Okay, so let me begin. Actually, we heard Pankaj talking about the digital engineering and digital twin technologies. And while he was talking about it, he shared a couple of aspects that digital twin is capable to deliver to us. And one of an aspect was like you can create a a virtual prototype or digital prototype of a physical machine, and do a lot of things with it. Like you can do an operator training, you can do the what if scenarios, which is called the simulation part also here, or you can use it for faster commissioning processes. So first, actually, what we want to show is that we have created a digital twin of a model that I'll show that physical model also to you. That is in our Gurgaon DTech center. We call it as a pick and place application, where there's a Fanuc robot which is picking and placing the objects, from an intelligent or independent track, conveyor system. You can see here we have an independent cart technology here, which is called ICT, or the latest conveyor, and there are some moving vehicles over it. This is basically based on the technology of linear synchronous motor technology. It has it has less friction because there are this is working on the basis of magnetic repulsion principle. So you can see these vehicles are the only movable parts on this conveyor, and each of these vehicle has a defined ID and the position which is known to the controller. So controller can direct this particular vehicle to move to the required path. Like there are 3 paths on the conveyor that you can see currently here. So path 1, path 2, and path 3. So we can have multiple paths or very complex paths into the system. And accordingly, knowing the mover positions, we can move them, we can target them just like a servo axis, and point them towards the required stations where some activity has to be processed. And also you can see that here it is equipped with some of the sensors here. You can see these are sensors which are actually sensing the height of the object and the presence of the object. And we are seeing all this in a digital environment here. A Fanuc alarmate robot is picking and placing the objects from the conveyor back to the station. Now, in case we have some data information is also available here, we're getting an time in state of the robot, that at what time, what functions it is doing, like going to the home or picking up extra. And we are also getting some analysis part, that what are the total number of parts being picked, or what is the ppm of the machine currently going on, and what is the machine health state currently. If I hit a push button, the emergency push button here, so you can see that the machine will come to a stop, and we will get an information that the machine front emergency push button has been pressed. So as a process, we press it back and we reset the machine so that it can start again. So these kind of animations can be incorporated into the digital twin, which is exactly same that you will see in the physical machine. So if I have an operator, he wants to see that what lies inside the machine components, he can hit in this box and open it up and see the various functionalities, various equipments, those are within the machine, within the panel, without actually physically going to the machine location. So we also have, some of the more animations that actually have been incorporated into this model. So you can see that there's a door opening which can happen here by hitting a door open switch, and this In an identical manner, the same thing happens here when we operate the physical machine here. So the machine would come to a stop condition. Now, when we close the door back, you can see the immediately as we hit the button, the robo will come to a stop position, knowing that the door has been opened. And the moment you hit the button back, door gets closed, and you can reset the system to start the machine again. So that's the process actually that runs, in the physical environment also, and we are simulating same thing actually here in the virtual environment. And if I want to see that how much is the ICT, which is independent car technology, I want to see the matrix that what is happening at the different stations of it. So I see a complete analysis from here, from the table, that which there are 3 stations currently, and I can see that which station is being more consumed or more utilized based on the job operations. So you can see that there could be a long process in a shop floor environment. And if you want to see that how the performances are going on at each station, we can check it from these matrix data and informations very easily. So this is actually the digital table of a model that we have created. So let me take you now to the physical the model also, which is actually available in our DTech Gurgaon office center. So this is actually the live camera view of the model that is working here, that I was just running in the virtual environment. Now this is the physical one. So as I assign a run command to this, I can give a run command to the system here, and you can see that with some countdown, the system will start functioning, and I'm all doing it remotely here. So the process is same. This is the same ICT conveyor, which is independent car technology, which is, as I said, is working based on the linear synchronous motor concept. And these are the moving vehicles which have defined ID numbers and defined position, which is known to the controller, so that they can be directed to the required paths here. And the Fanuc alarm meet robot is picking and placing these objects one by one onto the turret. So these are all the sensors that you can see in front here, which are actually sensing the height of these sensors, the color of these sensors, and presence of these these parts, so that they can be tracked and picked and placed onto the required positions as needed. So now if you see here that the sensor typically here, they are blinking here. So what does that say actually? In a machine there can be thousands of sensors. Now these sensors are IO-Link technology enabled, which means that they have communication capability where they can send the data on real time. They can send the information to us on real time. So if I have thousands of sensors on a machine, and I want to locate any particular sensor, I will hit a button from faceplate, and that particular sensor will start blinking, so that I get an information that like locate me kind of information for that particular sensor. Also, these sensors have capability, they have a window here. So we physically demonstrate that to the customer by placing some kind of paper onto the window sheet of the sensors, and we show that if there's a high dust accumulation of on these sensors, they give us an automatic alarm or alert that there's a high dust accumulation on that particular sensor, which needs some cleaning kind of activity. So that is the intelligence of the sensors that lies into it, and what they are capable to tell us about their the health also. They also tell us about the temperature, what they are facing, the running hours, how much they have passed, and the environmental conditions through which they are passing also during the operation. So this is the physical model which is available currently at our DTech center, and we have also created a digital prototype of the same model that I showed to you also. Now besides this, let me halt the system. Besides this, what we can do from the digital engineering also, we can do the operator training. So let me just show a small video here. If you see this particular video here there's an operator who has put a virtual reality gear set onto the head, and this is a semi-automated machine where he's getting instructions on the left-hand side screen. that which part he has to pick first and how he has to place. So if there's an operator or a new journey and he want to get acquainted with the machine, he can get well trained using the virtual reality of this digital twin software, and it guides him that which bearing part he has to pick, and the pink shaded portion on the object there shows that how that particular object has to be placed. So this ensures that the part is picked up correctly, placed correctly, and once an operator does it for several times, it is sure that he will not commit any mistake onto the physical machines because he gets well trained onto the system. And in the virtual world, if he commits any of the mistakes, for sure there is no damage to the mechanical system or machine or any possibility of injury to the personnel. So this is the how the operators can be trained onto this system using the digital environment. Besides this, we can also create a what if scenario. I have one more model that I'll run here, which is giving us an information on the what if scenario. Like I have simply a couple of conveyors where some of the robots are picking and placing the objects, and there is one forklift which is picking and placing the objects from one point to the end destination. Okay, now but I don't know that how many forklifts are required here. Where I was designing the system, I thought that let me save the cost, and I used just one forklift. But when I shared it with the customer, with my end user, he said, no, I'm not getting the best performance or best analysis. There are 5 conveyors, so I should have minimum 5 of the forklifts, or I should have 10. That was actually building up my cost. So what's the real scenario that what I can do so that I can go back to the customers and I can tell them that, see, this is the best optimum performance that we'll get out of the system. So let me run a simulation, which is basically a what if scenario. We call it an experiment. I have configured this system so that it runs the configuration for number of vehicles from 1 to 5. And we'll see that what is the throughput analysis that we'll get. So we hit the experiment run button. The processes would begin. Initially, it will start the first, the run where the forklift is just number 1, and it will run it. We can define the run duration for which we want to run that particular experimental sequences. So now after that, the second sequence will begin. You can see that the number of forklifts is also changing into the scenario. Now you can have a third forklift placed into it so that the experiment third can be run here within the given time. Then we will have the 4 forklifts running in the same time duration. And finally, we will have the last one, which is the 5 forklifts, which are being simulated to see that how is the performance if I have five forklifts into the system. So once I complete the experimental process here, I get actually a kind of an Excel sheet generated onto the right screen here, and I can use some basic kind of Excel techniques to generate a kind number of experiments that I have done and the total value that is generated here, so that I can represent this in a graphical form, which gives a better understanding of the things that how the things are happening here, so that I can show to the customers in a much understandable order. Now, what you see here on the curve, there are 5 experiments being conducted, but if I have 3 number of forklifts, I'm getting the optimum performance. I'm getting the highest throughput. If I have less than 3 forklifts, the performance is poor. And even if I have more than 3 forklifts in the system, still the performance is not good, is poor. So if I go to customer and share this data, that this is the analysis that is available, and on this what if scenario basis, what we come out that you will get the best optimum throughput analysis, or you will get the throughput using the 3 forklifts into the system. So this is what actually the what if scenario of the digital model can be done, and we do not need to carry all these hardware stuffs to the customer. Just a small piece of software in a laptop and some kind of a program configuration running into the laptop, and show it to the customer that how the system has been designed and what performances it has capability to do it. Besides this, the what if scenario, we can also, as I said, that we can build some machine prototypes, or we can build the manufacturing line prototypes, and we can virtually walk into the plants. Like we can wear a virtual reality gear set onto our head, and then we can actually go see ourselves going into the plants. So let me show a very small video which is talking about that, how we can take a walkthrough through a small plant, which is basically a cookie line manufacturing plant. Is the audio, you can hear the audio also here?
No, Vijay, audio is not coming from this.
So
we are not able to hear the audio from this.
okay.
Share again
Yeah, let me share
with the computer audio.
Yes, while
Okay.
sharing, you can share the audio, then you'll.
Yeah. I got it. Now, you see, now I think it will be available. Advantage of digital
Is it okay?
It is not
Yes,
limited
yes, fine.
Yes,
where
sir,
we can create a virtual model or digital model. We can also create a model for a manufacturing plant. Like you can see
can
here,
you increase the volume? It's too
where we
low.
have created a complete, virtual plant where different sections of the plant are shown. So what I'll do, I'll take a tour of this plant and let me join. I'll just put a VR gear, and then we'll have an experience of the virtual reality where we'll be going to different sections of this plot and see the various sections. So let me open the VR mode. Okay. So here what we see is that we have a different sections of this plot located. So we'll be starting right from the mixer section, and right from the mixer section we'll go to the extruder section here, where you can see the cookies are being formed and they are conveyed over the conveyor. Then followed is the heating section where they are being baked, and then we have a cooling section of this plant. You can see different motors running here, different fans operating here to get the process done. Then after the cooling and heating and cooling processes are over, then we have the packaging section where you can see the cookies are being packed in the small boxes out there, and then moved to one more section where they are put in a gray colored box. Then we go to the next section in the packaging side, where these small boxes are being put in a carton. These are the carton boxes being filled up with these gray colored boxes which have cookies inside it, and finally conveyed to a section where these are being depalletized. You can see the system here is moving all the packets onto the conveyor. And once the process is completed here, then we go to the final packaging section, where the big packs are being wrapped together, and then we have a vehicle which is carrying these goods back to the stockyard. These are the places where the material is being stocked here, and this is done by this forklift, and we have different packages available. So this is the strength of the digital twin, that it is not limited only to the machines, but we can create a scenario for the the complete scenario for the manufacturing line, manufacturing plant also. So if I have created a digital twin of a manufacturing line, I can virtually take a walk through it, and I can even operate different machines locally into the section. So if you see, there are various screens available, and these screens can be actually made live, and the person can virtually operate that, or start or stop that particular machine, or see the data parameters, whatever he wants. Despite he is not in the plant, but he is making a virtual walkthrough by using the augmented, virtual reality technology. You can teleport to different sections in the plant and see how the process is actually working. Sorry, if it is integrated, then it will have a real-time data, real-time information that we'll be seeing here. So this is the strength of the digital twin technology that Pankaj was talking about. So in case there is any questions, please let me know. Go back to Pankaj.
Yeah, any questions from the participants based on the wonderful demonstrations being given by Pankaj, Abhirat, and Vijay?
One question: what is the approximate cost of developing these scenarios like virtual reality vis-a-vis the cost of the actual project?
Yeah, when it comes to cost, Pankaj, are you there?
Sir, are you talking about the cost of the solution?
Yeah, cost of the solution, developing the solution, and before the actual execution of the project.
Okay. So sir, for simulation, it would be near about 20 to 22 lakhs. Hello.
Okay, thank you. Thank you.
Any
Okay.
other question? Okay, if there are no more questions, thanks Pankaj, thanks Abhirat, and then Vijay for this
Thank you
wonderful
so much.
demo.
Thank you.
Thank you so much.
Thank you, sir.
Thank you, Dr. Shah.
Thank you. So certainly you got a 360-degree view of the various technologies that will be helping us in developing the smart machines. Then we also seen the virtual view of a complete plant and implementing the digital twin concept. So certainly we have few more sessions aligned in the course itself, which will be taking you little deep dive into the respective technologies. So certainly this session cover up in a wide spectrum of the technologies involved in creating a smart systems, and then how they can be done, what all platforms will be available. That is something as a subject of deeper learning. So that we will take you through as the course go along. So I think with this, let us continue the remaining part of the session that I will be discussing more on the technologies that we will be talking about implementation for the smart machines, and some experiments that we are doing in FSM on the development of these technologies that I will be sharing with you. But before taking session forward, let's do a small exercise together. Actually, that is what I always look forward, because you have heard about the smart machines, plant, smart products, basically. So what I will do, will have a quick discussions, and I will be noting some of the key points over here related to the smart machine concepts actually. So let's do this exercise, and let me share my iPad screen. Yeah, so what we will do, we will at least try to compile our wish list for the smart machines. And certainly from a rich experience that you are having working with the various machines, understanding the technology, certainly the technology portfolio is quite big and large, and there are plenty of options available to implement the same. But we should be able to derive based on your inputs over here, and then we will be having a subsequent discussion on those points. That is the idea of this session that is left out now. So as a smart, because all of you are familiar with the machines, you are working with the machines day in, day out. Can we start thinking about whatever has been explained in the previous session, and based on some of your wish list and understanding about the whole system, what are the features that I would be looking forward in a smart machine actually? So unless we understand that, unless we evaluate what exactly it is going to give me the benefit, there is no point talking much about the technology, because unless I am convinced that I am going to make some system smart that is going to help me and providing services differently than what I am getting today. So let me know one by one, whoever is interested to share the wish list, and we'll be compiling at least 8 to 10 points over here for the discussion further. So for any machine that you can talk about, whatever experience you have working with those machines, as if you want to make that machine smart, what is your wish list? Forget about how it is being implemented. We'll talk about that later on. But let's write down what are the features that we are looking forward.
I am Alok Mishra. I will like to have what we are seeing, like in coach in trains. What we normally do, we ask human beings to go beneath the trains and look for any missing part or anything hanging over there, if something is hanging from a coach or something.
Correct.
Or and then we have to see the temperature of the bearings and everything. So if all those can be captured through thermal imaging, or just like you have shown that one of the videos in that in which the machine, it was showing that one gear was getting hot, or it is having some problem.
Correct.
So if we can use an array of some sensors and under gear, basically it is in railway terminology, it is called under gear inspection.
Okay.
So anything which is not visible to a person standing on a platform, that has to be actually seen from below.
Okay, so I just note down this point, what you have mentioned, smart monitoring and inspection systems. I think that will be covering what you are mentioning under gear inspection requirement. Yeah, I think that is right.
Recently, one accident has also occurred in which one of the traction motors of that had fallen down, and it could be detected for maybe some few kilometers, and then ultimately it resulted into a major accident.
Correct. So yeah, thanks for giving this input. We are looking forward for such kind of a system which will help us in making system more safe for the human to operate, and certainly for the whole system as well. I think that's a good point. So we are looking forward for the safe or the smart monitoring and inspection system. That is one input I got right now. In terms of the equipment or the machines or the system as whole, if you can recommend something, you can also recommend something maybe futuristic. We are looking forward that, yeah, if this kind of a smartness is available with the machine or the system, it will be helping a lot, either as Alok has mentioned about the safety parts, maybe the similar more advantages in terms for the user as well as the people who are operating the system, maybe for the customer as well. So can we have more inputs?
Can I add one more thing? I'm Alok again.
Yeah, Alok.
Apart from this, one more aspect is there, that we are using wagons for loading of coal, iron ore, and open wagons. And what happens when they are going, they are sent to loading sidings. There they use some JCB machines and everything, and because of that, the wagon bodies get damaged. So if we can we can have a comparison between incoming and outgoing rakes, so that we can know whether when the wagon had gone there, then it was okay condition, and when it has come out, then it had got damaged. So if that can be automated, then it will be of help, and then corrective actions can be taken regarding.
You mean the inspections of the wagon basically while they are going inside and then they are coming out, and then comparing the two conditions basically.
Basically profile of that, because bulging of wagons occur, and that makes it unsafe also.
Yeah. So I think the previous session where Sudhanshu was explaining about the sensing, and certainly he was discussing about the bulging problem of the wagons. So maybe some advanced sensing or the smart sensing can be implemented, which will help us.
He had covered, yes, he had covered that point in there.
Correct. So good input. So I'm still looking forward for more ideas because we have a good team over here with a rich experience working in the different systems. So please come out and share with us this list so that we can have a further discussion on that.
Sir, one more item is there. Actually, in railways, we have a lot many rolling and points. Like in one yard, once the rake is entering, a team is there on both the sides to check whether some unusual thing is there. Like whether sir has said that under gear some hanging parts are there, or some hot axles are there, or some major damage are there, or some unusual sound is there. And again, after the readiness of rake, there is rolling out. So a lot of manpower is engaged in railways for doing this activity only. So can we have an integrated system for rolling in, rolling out, which can measure the axle box temperature, which can notice the abnormal sound from bearing, or which can detect wheel profile, and it can also detect some undergear hanging part or some missing part or any kind of abnormality, basically while the rake is entering into any yard. So an integrated system which can do a lot of things as a human can do, because even if one factor is one parameter is missing, we have to deploy manpower.
Okay.
I hope I'm making myself very clear. So a system which is so smart that it can at later stages can eliminate the manpower, as the manpower is very critical in railways, and the manpower is getting reduced day by day. Anything that, like, we have some systems in railways like online monitoring of rolling stock, we have hot X or hot wheel detector are there, but they can't replace human intervention because they are getting only one aspect checked. So can we have some integrated thing which can do a lot of things?
So you're talking about a comprehensive system for this, no? I think that is
A
what
comprehensive system for measuring any abnormality, comprehensive system for maybe you can call for which can measure any abnormality, means any unusual it can notice and send information.
Good. I think these are coming out as a very nice ideas for the compilation of the whole project. The idea behind generating this list is that we should understand which all technology, which all sensing, which kind of solutions can be built around what are the existing problems. So certainly, I think these ideas, what you're coming out from your practical understanding of the situation, and that's why I'm just writing them. So comprehensive system for abnormality detection, actually, I think that is one. So it's basically combining the various inputs, sensing all together to detect the kind of situations you are mentioning. Yeah, that's nice. So I'm still looking forward for more points from a machines or the manufacturing point of view. Anybody would like to say these are the points which are from the inspection and the operations side? Anybody would like to give inputs from the machines point of view and the manufacturing facilities that you are using? What kind of smartness you will be looking into that? Because when we talk about smart manufacturing, certainly machine is a very important element of that bigger smart manufacturing. So unless we start making those small systems smarter, we may not be reach out to our the goal of making a smart facility, a smart factory, or the Samarth Udyog we are talking about. Anyone come from the other maintenance problems? Certainly these two are related to that only, but still some more inputs. What kind of challenges are maintenance and what kind of smartness we are looking at? Maybe some of the use cases based on what has been shared in the previous presentations, because I know that Surikant was asking about the AR. So is there any use case you have in mind, basically?
One more thing, sir, I want to add is that we normally in railways, what we maintain machines is like they are decided periods after which we have to maintain.
Correct,
so from
correct.
that, if you want to shift to condition-based monitoring or maintenance,
good.
then it will be a huge saving for railways.
Yeah, certainly. So this is one of the important technology, and then I should say the always in the wish list of the implementation of smart manufacturing, condition-based monitoring, and then the maintenance, basically. Yes, Surikant, you are saying something?
Sir, actually, in my workshop at Mumbai, there is a practice of painting the coaches. In this activity, actually, it's sort of a health hazard for human beings because the material that we are using is PU paint. So even one cannot actually stand in front of that area where this painting is going on, but still it has to be done. So we are looking for some solution of automated painting. Actually, sir, they have paint booths also. Some very paint booth technology is already available, where very big sheds are available, and then coach enters that particular shed. Then there are various paint guns also available, and after that, one more shed is there for heating this entire coach again after painting for drying purpose. But sir, that is again an investment of huge infrastructure actually. So we are looking for some kind of whatever we have seen in your presentation, sir, some kind of robotic arms or something which can paint it.
Certainly, when we talk about the technologies, there are a lot of trade-offs to be looked into. When we talk about the robotics, certainly we are talking about more customized operations to be done. And when we talk about the mass activities or mass production activities, certainly the robots will not be but certainly the robots are also being used in painting in automotive industry to a large extent. So I'm understanding that the kind of size you are talking about in your manufacturing is much larger than what an automotive industry is doing. But similar solutions can be thought through about the implementation in your use cases.
Yes, sir.
Okay, good.
Can I add to that, sir?
Yes, yes.
Actually, I am in Rail Vikas Nigam Limited, and we are already executing such projects. Like in Sonipat, we have recently commissioned one workshop. In that, we have already provided full paint booths for painting of complete coaches. And it is an automated system. And then again, one more workshop we are going to set up at Jhansi. In that, it will be a fully automatic robotic kind of system.
Correct.
Which will paint the systems are already there and we are using it.
Okay. So yeah, certainly, because these technologies are already well known and automotive industries are using it to a great extent, because the kind of volume they are dealing with and the kind of painting requirement they are already using a robotics technology. Certainly what you have mentioned is important, that you have to just make use of those technologies for the railway systems. Good. So let me talk about a few more machines that because let me talk about the manufacturing facilities, and you are dealing with the CNC machines, the lathe machines, milling, grinding, boring. So all that kind of machines you are dealing with, you may have some kind of issues with those machines, and certainly you may look forward for the kind of example I have given about a lathe machine. So can you just suggest something more about those machines? What kind of additional smart features that you are looking forward that will help you in at least taking care of the quality, the quantity, the maintenance, all other issues? Anybody would like to mention something about them?
Yes, sir. Sir,
Good afternoon, sir.
Good afternoon.
Sir, failure of overhead cranes are a major problem in my area, sir. Manufacturing of wagons, sir. So, sir, could be design something about it so that where the failure has occurred, because to detect the failure, one has to go to the machine and then search for the travel areas.
Correct.
Could it be detected?
Yeah, certainly that's a very good input. And in fact, I have a subsequent discussion on that, how you can build an expert maintenance system. So I think the combination of the multiple technologies put together will help you in at least early detection of these kind of scenarios. And then how, once you detect that, once you do the fault diagnosis, how you will be able to handle that. So that's a good input. I will discuss in the coming slides. Yeah.
Thank you.
Thank you. Anybody else? Yeah.
Sir, I want to add something. Actually, in railways, the rolling stocks are subjected to continuous cyclic loads.
Okay.
And there are so many welding joints, which gets deteriorated over the period of time. One term related to the cyclic load is the fatigue failure.
Correct.
What happens in railways that after failure of a component, we analyze about the fatigue failures and failure of welding joints. I want to know that there must be some smart sensors to analyze in situ the status of fatigue level or the condition of the welded joint.
Okay, good. I think that's really nice. I think this is really a very good input, how you will be able to judge the state of the welded joints and based on the fatigue loading that you're talking about. Yeah. Good. Anyone would like to add to this list? We are almost left with one or two more points to put into the slide.
Yeah, good afternoon, sir.
Good afternoon.
Sir, I want to add that our machines are not flexible in their productions. They should be flexible. Right from damper testing or some type of testing machines, we have to feed data that this type of damper is being tested or this type of spring is tested. They should automatically detect it, and all the result and parameters should be shared to the central servers so that analysis should be done easily.
Great. Yeah, this is really a nice idea. Yeah, the flexibility in the existing machines actually. When we are certainly see there are some situations, some problems we are already dealing with the conventional machines right now. But when we are talking about smart machines, smart systems, we have to make systems more adaptive to our needs actually. And we are looking forward for more agile facility. That is what I was mentioning in the characteristics of the smart manufacturing. So when we were discussing those key points or the key characteristic of the smart manufacturing, we have to think from that perspective as well actually. Certainly we have to solve the existing challenges. That is one part of the role that the technology is going to play. But over and above that, we also need to think about what kind of futuristic system should be there. So when we talk about the agility, we are certainly looking forward for more flexible systems. So many times we need that if I can have a wish list that for making even a component actually in any of the machine, for example. So I have to go through all the process of the design, then generating the part program, and then taking the job to the CNC machine. Then we have to run the program, and then there's a lot of steps involved. And in the futuristic way of manufacturing, actually, people are looking forward that if you just give the inputs for making a component, actually, rest of the operations or rest of the planning can be done by the system itself. So how can you do a better design and how you can basically do a better manufacturing with this kind of technologies? So the flexibility of the machine, the programming of those machines, certainly if you see that the conventional way of generating the part program, writing the part programs, many times if you are dealing with the robots, actually you need to write a program for every different job that you are looking forward. So there are a lot of innovations are happening in these areas that the minimum human intervention should be there in at least making the machine doing that particular job. So this flexibility of machine is certainly a very good idea in this case. Yeah, so I just note down that part.
I have another idea.
Yeah.
Utkarsh here.
Yeah,
so many of our workshops and production units are having very expensive machining centers and machinery and plant. Sometimes these go out of order. And since they are so complex, like let's say KUKA robots and all that, we have nothing to support within the country. So in the very beginning itself, at the time of procurement, we should build in augmented reality based
wonderful
maintenance and repair facilities.
Great. I think that is what I was looking at, these kind of inputs, and they are wonderful. So we are all aligned and thinking in that direction, basically how the technology is going to facilitate us in building and smart systems and smart machines. And as you are rightly pointing out, maintenance is a very painful area. And when we are talking about the complex systems and complex machines, rarely we have an expertise available with one single person to understand all the perspective of the whole machine. So that is the idea I was just looking at. So let me just share with you quickly this slide where we will be discussing on this. Yeah. So this is an important slide. I just want to discuss in this direction, and there's a lot of development activities we are doing in this direction. Idea is that how we can build an expert maintenance system. So why we would like to build an expert maintenance system? Because you all have realized and you have mentioned about these aspects that when we talk about any complex system today, or when we talk about any machines today, you'll see that it comprises of multiple subsystems in action. So any of the machine you are thinking about, as you have mentioned, that whether it's in a robot, whether it's in a CNC machine, or maybe the complex production systems, there are mechanical systems. You all understand the mechanical design, mechanical components being involved, mechanical subsystems are in operation into the machine. So some sort of information to be known about the mechanical system, because if something fails in the whole machine, how I will be able to locate which component it is and where it is in the machine, and then how it can be replaced, what kind of repair is required for that. Then we have a similar electrical systems in parallel, because if we have a machine, certainly we have an electrical components inside the machines. They are all wired together into the panel. Now, whenever person going to attend the maintenance for this particular machine, and there are variety of the machines. Again, the most important part is there is a variety of machines. How the person will remember, actually, it's very difficult to remember, say, unless he gain a lot of experience operating or working or maintaining a particular machine, he may not have an immediate idea actually. And many times you realize that the time to locate the fault is the much larger time. And then certainly once you are able to locate the fault, then rectifying the fault maybe another exercise to be done at the earliest. So in that case, what I'm just trying to bring out the point over here, that in any of the machine you are talking about, these are the common subsystems in all the machines. So you have a mechanical system, you have an electrical systems, you have a control systems in action. And the more and more advanced machine you are looking at, they also have a communication system. There's a lot of network being involved in the whole machine itself. In fact, this is one of the machine example I was just showing over here. This is a machine that we designed in our lab. So we have almost all the devices on the network over here, whether it's in a drives, whether it's in a sensors, all are using some kind of a network connectivity. Many times it fails somewhere in the machine, and then you don't have any clue actually why it is not working. So the idea about the communication systems is again an important part. Then certainly depending on the machine, you may have a pneumatics, you may have a hydraulics. Having the knowledge of all the systems by one single person who is doing the maintenance, or sometimes we have two people who are doing electrical and mechanical maintenance, is very difficult in the case of current scenario. So what I'm just proposing on the right hand side is the way the technology can help us in creating such kind of an expert maintenance systems. What we are trying to do and what we need to achieve is that, first thing is that because we would like to process information more digitally. So that is what is the important part. Whenever we do maintenance, we are dependent on the information that is available on the papers today. Sometimes it's a learning that has happened, and it's always with the person that who is having a knowledge about a particular systems. So we have to digitally represent the information about the system. That's the first thing. How you can represent the mechanical system, we all understand once you have a CAD drawing, it is being represented in a digital form. Are we having a system to represent this information in the same format in when we talk about the electrical systems, control system, communication systems, and the pneumatic and hydraulic systems? Sometimes we have, sometimes we don't have actually. So even the schematics that are being created, they are being made available in the form of either a PDF files or the printed circuit diagrams running into the multiple pages. So if I have to repair or maintain a new machine or any system which I'm not so much familiar with, it's very important and it's very time taking, I should say, that to trace out the whole circuit diagram and then narrow down into the location of the fault in the panel. So this is the something very important. The first step when we talk about the development of expert maintenance system is to digitalize the information about these subsystems, so that after we have a digital representation of that information, whether it's an electrical CAD, mechanical CAD, or maybe the PLC logic that you have written inside the controller, or the network diagram or network connectivity of the machine, I should have a digital representation of that information. So I will be using technologies how to bring everything on a digital platform. That's the first step. And then I will be also generating a real-time data, because we all understand that how the data being generated from the sensor, and then we will be bringing out the real-time information. So that is how I am adding an IIoT component over here. So there is some static information about the machine which is available from the various subsystems, and then there's a real-time data that is coming through the IIoT. Now these together will make a real representation of your actual system. Now what to do once I have everything on a digital environment, digital platform, digital representation of this information? I will be running some algorithms or the software environment basically, which will be helping me in continuous analysis of the system behavior. Now, how the machine is performing, how the machine is behaving, if there's anything which is not working as per the requirement. So this kind of anomaly detection can happen by these algorithms. So there comes the role of the technologies we will be addressing in the smart manufacturing is the cyber physical systems, understanding of a digital twin. So Pankaj has demonstrated some of the digital twin. We have a dedicated session on the digital twin, which is a very important technology built over the sub technologies, basically, whether it's an IIoT, machine learning, or the CPS or the analysis. All are put together in creating a digital representation, and digital twin is such representation of this machine. So then you will be able to run various scenarios on this digital twin and get to know about the system behavior without even doing those experiments on the actual system. So this is the one which is very important over here. Unless you have this available, you can't go to the next step. So what idea is that once we are able to bring out all the information in digital form, and then we will run all these algorithms to analyze the system behavior, whether it's an electrical fault. So we have done that. So how you will make the electrical CAD available in the format, or electrical panel diagram or the wiring diagram, in such a way that my algorithm can analyze actually. So if I'm not getting an appropriate data from a IoT, immediately I should look into the circuit diagram actually. That's the normal way we use to address the problem. So for example, any sensor is faulty into the whole machine, immediately I will be stop getting some of the IoT data. And once you are not getting that IoT data, then next task is to basically analyze the circuit diagram to narrow down into the region where the fault is actually. And that is how it is possible that once you do this kind of analysis on the digital data that is available about the machine, and IoT is only giving an immediate indicator that something is not working properly and something is working properly. So based on that, you will be dig out that information through analysis. So once you are able to do this system behavior analysis and the fault diagnosis about the machine, and because this has to run through all the systems mentioned over here, it's not being possible selectively that you will do the analysis on the electrical system alone. You may not be taking into account the control systems, the communication systems. Many times the faults are very small, but you spend a lot of time in locating the fault, where the fault is actually and what type of fault it is. The system is not working. That's the only symptom that we can see that. So once you are able to implement this successfully, the next part comes once we know that the fault is there, then we need to cut down the time significantly to address that fault and to do the repair of that activity. There comes the role of the technology, which we are talking about, the remote access and the maintenance part. And that is done with the help of the augmented reality. So augmented reality is basically guiding a person on the spot. That's how we will be looking deep into that part. Instead of searching the information here and there to do the maintenance activity, it's all trying to bring out in one converged view the physical system as well as the digital information, so that immediately you can start doing the maintenance. You may not be looking forward for additional information to do that particular maintenance activity. So there comes the role of augmented reality. So if you look in totality, there's a continuous analysis of the system behavior. There's a possibility that your system will be able maybe go into the fault, and then fault diagnosis will happen immediately. And then based on the digital information, I will be able to locate the area or the component which is faulty. And once you are able to locate that, then I will be run through the sequence through the augmented reality to rectify that fault. So I will be assisting someone, basically a maintenance engineer only or maintenance team to rectify that fault. We will be able to save a lot of time in diagnosing the problem and then repairing the whole system. So if we are able to build out this kind of a system with the help of the technologies that we are talking about, certainly that will be a kind of a boon for the maintenance. That is what our understanding. We are trying to implement these individual technologies that we have mentioned on this side on some of the systems in our lab, and which is very important. Basically, that is what I'm just trying to convey and share with this particular slide. Any quick input or suggestion, and that you may be able to correlate some kind of a scenario with this discussion which we are doing right now? Because I see a lot of I think participants are into the maintenance. So if you see that, is there any challenge in implementing this, or is there something new to be think about in this kind of implementation? I think those inputs are really helpful.
I want to add, sir, one thing.
Yes.
That, lot of research and everything is going on, and there are many solutions available in market. But what happens is that when we go and search for machines, even now in India, we find that most of the machines are just traditional machines, and here and there they incorporate some sort of maybe digitizing those signals and all that. A complete implementation of almost all of the things available is not being really focused on. Still, people are supplying machines that are typically a traditional mechanical system.
Correct. So I think only point I would like to tell on that is it's a kind of a journey that people are not going to change immediately, or the systems are not going to change immediately. It's a kind of a journey that slowly we will start implementing those. As you rightly said, that most of the things are in research actually, because even the Western countries who are developing these technologies are doing a lot of research still, even after they are talking about Industry 4.0 almost 10 years, more than 10 years now. So what opportunity that we have is that once we are able to understand the technology rightly, we are in the same path actually. We are able to build the systems for our own manufacturing setup as well. So that is the good point, that the technology, the information is available at the same time. While the people outside India are experimenting, we are also in the same boat, that we are also doing experiments and develop our own solutions. So that is something I always feel about the Industry 4.0. Someone else from outside may not be giving you the complete picture. This is something we have to evolve ourselves with the help of these technologies, how we would like to utilize them in our current scenarios. Good. So I think with this, let's go ahead. And this is another important part when we keep talking about the cyber physical systems. I would like to just brief about this, because when we talk about the smart machines, we would like to make our machine tools intelligent actually. And when we are talking about the machines, certainly we are looking forward for the smart factory. And the parameters of the smartness or the kind of intelligence we are looking forward is very well summarized in this particular slide from a research paper. We would like to make the system self-aware. And then we are looking forward that the system should be also able to predict something. That is what the self-prediction behavior is there. Then we are looking forward for the self-comparison actually. So if we have multiple machines at a different locations, the same type of machines basically, how the individual systems will be able to compare the behavior among themselves, and we will be able to learn from the failure of the other machines as well. So this self-comparison is very important. The same machines running in one shop, one plant, and the similar machine running at a different location, they are performing differently. The maintenance cycle of these two machines are different. The kind of failure happen on these two machines are different. So how a machine can benchmark and compare with the similar machines working and operating somewhere else. So that is also very important part. See, some of these technologies or some of the concepts, if you can see, it's all coming from the human being, basically the way we are trying to compare the performance among ourselves. Same thing we are looking forward that the same approach will also be implemented for the machines. And then lastly, as we are talking about the adaptability, actually the adaptation parts, we will be looking forward for the self-configuration actually, to make the systems more resilient for the dynamic changing environment. So when we talk about the cyber physical system implementation or the CPS integration, we are looking forward for these different levels of implementation, or these different this is what is known as architecture of implementing the CPS. So in this case, they have explained the 5C architecture, and this is very popular and the common architecture when people are implementing cyber physical systems. So I just want to brief you about that. So it all starts with the connectivity part. That is what we were discussing. So connectivity means connection when you made and you have all the sensors in place, and this is going to give you the services of the condition-based monitoring. That is what the starting point. So instead of going with the preventive part, and as we have already listed out in our wish list also, we are looking forward for the condition-based monitoring. So when we are looking forward for such implementation, understanding of a CPS is very important. So our first layer starts from the connectivity layer, and then based on the sensor integration and the communication part, we will be able to implement the condition-based monitoring. Post that, after you have all this information coming from the different sensors, now we will be talking about converting this raw data into the information about the machines actually. And that is where we are talking about more subsystems and the machine as a whole, and would like to utilize this information to make the machine self-aware actually. So whether it's in a wear and tear, whether it's in a deterioration of the component, and as some of you are mentioning, the fatigue, failure of the welded joint. So how we can be reaching to the stage of the self-aware, how the system will be aware about that, yeah, this particular joint is now going to fail, these kind of cracks are being developed, or this has a certain fatigue life left out. So this kind of an implementation, we categorize them in a self-aware situation. Then we are talking about the next level, that when we can compare the performance among the similar equipments actually. So that is what the similar machines elsewhere operating, and how we can keep the snapshot of the machine performance over here. And that will be taking you to the stage of self-comparison. And this is only possible when we have a connectivity and between the machines, the fleet of machines. Basically, when we are talking about the fleet of machines, this is again a very important learning, because we can't keep waiting for one single machine to fail and then we will be able to get to know what to do with this particular machine and how to predict that actually kind of failure. So the learning from same fleet of the machines placed anywhere, and they are operated in different environments and different conditions, it will be in a common learning for all the similar systems actually. So that is what we are trying to implement, the cyber layer, which is helping in implementing the self-comparison. Then we will be developing a cognition layer over here, which is a kind of a decision support system based on the learning that has happened between the comparison between the multiple machines. Once the machine are able to generate a knowledge and a know-how basically. So then we will be able to take a better decision, and a proper decision support system can be built on top of that. And lastly, once the decisions are being implemented and thought about, so as we are talking about the fault diagnosis and we are talking about the system behavior analysis, all that can be done. And lastly, the reconfiguration of the machine by themselves. That is what we are looking at, the last layer of the CPS integration, is that how you will make the system self-configurable actually. Also, that is what the minor changes can be done by the machine themselves before it comes to the final failure state. So if it is requiring some kind of a tuning, can the machine will be able to tune these parameters on its own. So if we look forward that if we start implementing the CPS, we will be able to implement all these characteristics over here of the CPS system. And once we are able to do that, we will be certainly building more the machines more resilient for the dynamic changing environment. So that is the idea of the CPS I wish to share with you in this course. So I think we are slowly building up. So as a part of this course, we all started learning about the basic concepts, and slowly we are building toward the course, and we will be going little deeper on these individual technology elements. And then bigger goal, as has been explained on the day one to you, that if we start correlating with the existing problems or existing challenges as a part of your project actually. So the basic idea of these 2 days is to initiate that understanding, initiate that the learning part, so that you will be able to understand the technology piece. At the same time, you'll also be able to understand what are the existing challenges and how you will be thinking about solving those challenges. We can have more and more hands-on sessions. Certainly that is the preferable way of training I always used to conduct. But in the interest of time, it's very difficult to go too much deep into the technology implementation part. We may explore those kind of possibilities with the selected group who are really keen to go for the implementation, because we always mention that initially you have to build the awareness and the knowledge, basically how we will be approaching a problem. And slowly, once we are clear on that aspect, then comes the implementation layer. So as we go along, we keep on giving you some demonstration, but that small demonstration, I understand, may not be sufficient enough to start implementation, but that is good enough to at least plan how we can do that implementation. So that is all from my side for today's session. We are almost at the end of the time.